So we are starting the presentation. Can everybody see my screen? Excellent.
Yep.
I'd like to welcome everyone to the second annual Earth Day 2021 webinar titled Energy in the Pandemic Era. Our co-hosts will be myself, Scott Sherwood from Echo Care Corporation, and Matthew Rubenstein from Blue Green Group. I'm going to go over some information, some rules. I want to remind the audience that there's 4.5 PDH professional credits. I want to thank the New York ASHRAE Board of Governors, the Sustainability Committee, and especially the chair, Ed Bricker, for their continuing support for this Earth Day annual event. If there are any problems through the webinar or any of the presentations, please email either Matthew or myself, and we will work with you to rectify the situation. Let's go over the rules, the audience questions. Please post your questions in the meeting chat directed at the operator, not at the speaker or panelist. The operator will be myself, and there I can feed them to the speaker at the time. Please identify the specific person. If you have a person that you would like to answer that question, most questions I will have a couple of the presenters answering them so we can get some different perspectives. Like I said, there are 4.5 PDH credits, one for each presentation and 1.5 credits for the panel. And if the audience would please be sure to watch the entire segment so that they can get the credits afterwards. Once again, if you have any problems with the stream, like any virtual meeting, please disconnect and reconnect. And if still trouble, restart your browser or restart your computer. If you still can't reconnect, you can call us on our phone numbers from the meeting in your invitation email, or you can email Matthew or I. I'd like everyone to remember, I'm sure I don't have to remind you, that Thursday, April 22nd, is the 51st anniversary of Earth Day. It was begun in 1970. I'd really like to make this entire webinar's theme about the balance in our environment. I think it's pretty obvious to everybody that parts of our environment are out of balance. I believe the pandemic has brought this to illustrate exactly what can happen when that balance is affected. And I really believe the way to bring our environment back into balance is for all of us to practice sustainability and resilience in all that we do. The time is now for change. As the world was locked down in 2020 and into 2021, the climate crisis has continued. It has even accelerated. The polar ice caps have continued to melt, unfortunately faster than ever before. Temperatures continue to increase. Oceans continue to acidify. Deforestation soared to historic levels in 2020. Obviously, we were all not locked down. And climate change is not an on-off switch. You cannot just turn the switch off from the damage that is occurring. It will go on for years, possibly decades, after we rectify the damage we are creating by the pollution in our air, the pollution in our water, and the overall destruction of many of the carbon sinks, like the forests and the oceans. But change is happening. There are positive signs that society is getting the message. In 2020 alone and 2021, we're witnessing tremendous innovation, especially in vaccine development and sustainable resilient technologies. As Vice Chair of ASHRAE's TC 2.5 Global Climate Change, I am so proud to share that the TC completed and will soon publish the first Global Climate Change chapter handbook. Actually, on Thursday, our chapter handbook chairman, Elizabeth Tomlinson, will be issuing the report prior to it being published in the handbook. And if anybody would like a copy of that, please email me and I will make sure you are provided one as soon as Elizabeth sends it out. In 2020, we also witnessed how ASHRAE became the predominant voice and opinion on airborne infectious diseases. In effect, how to contain SARS-CoV-2, COVID-19 in our buildings. That effort is led by ASHRAE's Epidemic Task Force, the ETF, and the ETF is chaired by our second presenter, Bill Bahnfleth. And we are very pleased to have him and thank him for the time that he has taken for him to lay out ASHRAE's current core recommendations and explain them to us. So when does change happen and who is responsible? We can see in the media that everybody is pointing the finger to everybody else. Well, change happens when enough people understand the issues and are willing to work together to solve them. And we are all responsible. We are all members of the society. We are all responsible for what happens. Now, I took this next picture at the beginning of the pandemic. The fearless girl that stands across from the New York Stock Exchange was wearing a mask when I got there, and I took a picture of her profile to show how bold and fearless she is. She represents us. She represents all of us in society. But in 2021, I was recently back down to the Wall Street area. I took a different picture because I believe in the future, and the future is today. We all need to stand together to change that future going forward. For ASHRAE, change means buildings, and that means designing more sustainable and resilient buildings. The focus of this webinar will be how to accomplish that. And with that, I would like to introduce our first seminar, Energy and Carbon in the COVID Era, Lessons Learned on Balancing IAQ and Buildings. And that will be presented by Molly D. and Jonathan Lee from Jarvis, Baum & Bowles. And I'm going to turn the screen over to Molly and Jonathan and welcome them and thank for their time. Molly, Jonathan.
Thanks, Scott. I don't yet see the share your screen.
I am going to change the presenter. And how is that?
I believe that should do it.
Excellent.
Can you see the screen currently?
Yes, we can. Thank you.
Great. Well, thank you for that introduction, Scott. That was great. And good morning to everybody. Just some quick introductions before we jump into our first webinar, which Scott introduced. My name is Molly D. Ramasamy. I'm the head of deep carbon reduction at Jarvis, Baum & Bowles, and I'm here with my colleague.
Hey everyone, I'm John Lee. I'm an associate in the HVAC department at JB&B.
And we're here to talk to you today specifically about lessons learned on balancing indoor air quality and building performance. So with that, I'll just quickly give an overview of what John and I are going to be speaking on, and then we'll move right through the presentation with some time at the end for questions. But essentially, John and I were privileged enough to work on an interesting study to evaluate the energy impacts of some of the early core recommendations from the ASHRAE EFT in relation to COVID mitigation. And that's going to be the content of this presentation primarily. So we're going to talk about sort of the landscape prior to COVID in terms of sustainability and energy, Then we'll move on to how COVID shifted the conversation and the focus in the built environment. And then finally, we'll turn our attention to the study that we conducted just across a sample of buildings in New York City to evaluate those energy cost and carbon impacts of those core recommendations that were provided early on. So to take a step back before we get into the hard data and the research, I think it's worthwhile to talk a little bit about what was happening in New York before COVID took over in late 2019, early 2020. And there was a big conversation happening at that time around energy policy and policy as it relates to carbon and carbon reductions. So what you're seeing on the screen in front of you right now is sort of a honeycomb graphic of the different policy initiatives that were either in place or expected to be coming down the pipeline that were really a core center focus for people in the built environment here in the city. Of course, the primary attention grabber at that time and conversation starter was around the Climate Mobilization Act and the passage of Local Law 95 and Local Law 97. So to spotlight those a little bit, just for anybody who may be unaware, Local Law 97 is a carbon emissions cap law that was passed in 2019, and it was really the first policy of its kind. The impact to the industry was anticipated to be widespread and very meaningful. From a financial perspective, it was estimated by Urban Greene that as a result of Local Law 97, there would be around $20 billion worth of anticipated investment in existing building retrofits and upgrades to meet this new stringent carbon cap law. Additionally, we had Local Law 95 hit the streets. This is the energy efficiency and letter grade law for buildings. So in addition to talking about how to reduce carbon in our buildings, there's also a focus on energy efficiency and driving down energy for better energy efficiency scores and letter grades. And then COVID happened, right? So tons of conversation about these policy initiatives, a lot of attention, a lot of effort put towards trying to kind of solve those problems with Local Law 95 and 97. And then COVID came into the picture and things just fundamentally changed, right? The focus of the industry really shifted from energy and carbon to business, to real estate, right? The state of our economy in New York City, and of course, health and wellness. How do we mitigate COVID? How do we protect ourselves and our occupants and tenants from this terrible thing that we're experiencing? And how do we keep our economy intact as we do so? So I'll turn it over to John to talk a little bit about some of the early guidance from ASHRAE that came out in response to COVID-19.
Yeah, so when COVID started, we looked at the different organizations like CDC, WHO, and ASHRAE, and looked at the core recommendations that they were, issuing to everybody. And we found that there was about 5 categories that were common across each of them, including increased outside air ventilation, temperature and humidity control, upgrading of particulate filtration, use of portable air filters, and also, in some instances, the use of UVGI.
So those were some of the early recommendations from these different governing bodies, and they've carried through. We're going to talk a little bit later on about how some of the guidance has evolved and changed over time, and I know that's something that Bill will be focusing on as well. But early on, this was what we were working with, and it left our clients asking 2 big picture questions, right? One, if the energy and sustainability goals of the city aren't changing or aren't slowing down in response to COVID, how much more energy am I going to be using by following this guidance in my buildings? And then the follow-up question to which is, all right, well, obviously health and wellness, we need to prioritize that, but is there a way to align energy and carbon with indoor air quality and health and wellness so that we can have the best of both worlds? And those 2 core questions were what really set the stage for the study that John and I participated in, which really set out to answer those 2 questions. And we approached this project in the following manner. We said, okay, first we need to understand the existing energy and carbon profiles in a sample set of buildings in New York. The sample we were working with, 10 buildings, right? So we're not talking about a huge sample size by any means, but we did do our best to bring in different kinds of buildings with different criteria and different systems to get a sense of what we would be working with, right? So number 1, understand the existing building energy and carbon profiles. 2, then through energy modeling, different strategies, evaluate the energy cost and carbon impacts of those core recommendations that were coming out from ASHRAE for safe reopening and COVID mitigation in our buildings. So I'll talk a little bit later on about how we did that and the process that we used. And then finally, step 3 was looking at all of the various different indoor air quality opportunities, improvement opportunities that are out there, and then finding ways to potentially combine them or stack them, optimize them essentially, so that we were looking to reduce energy and carbon, but still maintain that improved indoor air quality and safety. So in terms of project approach, I want to tell you a little bit about how we kind of went through this in each of our buildings, right? The first step was to do a field survey of existing systems. So we did go out to our sample buildings, we collected information and data about the systems, how they were operating, and then ultimately tried to figure out what was going to be feasible in terms of indoor air quality improvements, not just for the ASHRAE core recommendations, but for other indoor air quality recommendations as well that we'll cover a little bit later on. From there, we evaluated effective air change rates. The reason for that, and John will talk a little bit about that, was to do an apples-to-apples comparison against different technologies from an effectiveness standpoint. And then from there, we went into sort of a dual analysis, analyzing the energy and carbon impacts and also analyzing the financial impacts of potentially implementing these different strategies. The final step, of course, was to report, and here we are today sharing the information from this study with everybody on the panel. So John, why don't you talk a little bit about the effective air change rate and how that kind of fits into how we approached the study?
Yeah, so as Molly mentioned, we use the equivalent air change rate as the approach with the energy models to try and compare the core ASHRAE recommendations with some of the alternatives that we'll show later on. But the equivalent air change rate is a way for us to compare the different mitigation strategies or a combination of the strategies by evaluating the uncontaminated air being delivered within the space. The equivalent air change rate approach takes into account the actual amount of outside air and also the impacts on the filtration effectiveness on the recirculated air with the filters at the air handling units, and also any impacts on any sort of air cleaning technologies that we're using, either UVC or portable air filters.
Awesome, yeah, and this was a really important part of our study here, and you know, we were lucky enough to have some good resources and some thought leaders in the industry kind of putting forth different methodologies. What was particularly useful about this one, as John mentioned, is that it allowed us to do that apples-to-apples comparison between different kinds of indoor air quality technologies, right? Whether it's increased outdoor air, right, as opposed to an actual piece of technology that you place in a room, like a portable air filter or UV or something along those lines. So this was a really instrumental part of our analysis. I also want to touch on the energy modeling approach for a moment, just to sort of level set on how we evaluated the energy cost and carbon impacts of these different recommendations. So on this particular study, we use a combination of approaches. In certain scenarios, we used spreadsheet type energy models and actually built upon tools that had been put together by others in the industry in relation to ventilation air. In other scenarios, we used actual simulation tools for energy modeling, and we did this purposefully, this sort of mixed bag approach, to be able to compare and evaluate the different methodologies for evaluating the energy cost and carbon. So we were able to learn, I think, some valuable lessons, not just on the indoor air quality side, but also on the evaluation methodologies for how these things impact the performance of our buildings. So now that you know that's the sort of background on how we approach this particular research project, we're going to go ahead and talk about the details of the different recommendations that were evaluated, and then of course our findings. So again, I'll turn it over to John to talk through those core recommendations from ASHRAE, and we'll go from there.
Yeah, so just to clarify, right, the evaluation was based on the recommendations that were set forth by ASHRAE during the beginning of the pandemic. So some of these recommendations have remained the same, but also some have changed, which we'll talk about later on, and you know, in this webinar. But the core recommendations include increasing outside air, a flushing sequence within the space, increasing the filtration to MERV 13 minimum, and also disabling demand control and the use of energy recovery devices.
And for the purposes of this presentation, John and I are going to do a little two sides of the same coin bit here where he's just going to talk a little bit about the benefits from an indoor air quality perspective of the recommendation, and then I'm going to follow up with the energy impacts just from a high qualitative level.
Yeah, so just to recap on some of the principles behind the initial core recommendations, increasing ventilation air. By increasing the system air ventilation, it reduces the recirculation back into the space and diluting the concentration of potentially harmful or undesirable compounds that are suspended in the air. This would result in a lower concentration of airborne particles. And we know that the limitation of this strategy is really the capacity of the heating and the cooling coil of the air handling unit, and this was taken into account in our model.
Yes, and from the energy perspective, while we have the benefit of the reduced concentration of nasty airborne particles, right, to John's point about coil capacities, as we're bringing in more outdoor air, we're inevitably doing more heating and cooling of that air. And so that comes with an energy impact and energy penalty. Moving on to the pre and post occupancy flush.
So the intent with this, with the pre and post occupancy of the space or flushing of the space, is to remove any of the harmful or undesirable particles that may be generated in the space while the space is occupied, with the outside air being provided in the space, and also with the assistance of the filtration at the air handling units.
Right, and then again, from the energy perspective, still additional heating and cooling most likely required, and then we're also thinking about additional fan energy to move that air more quickly and more frequently throughout the space.
And arguably the most popular and probably well-known ASHRAE recommendation is the use of mechanical filtration with a minimum of a MERV 13 efficiency. We found that MERV 13 and greater filters or more efficient filters are effective at removing particles in the 0.3 to 1 microns diameter size particles, as you can see in the table. But they're also effective, or even more effective, at removing particles at the 1 to 10 microns. Even though that we know that the SARS-CoV-2 virus is around the 0.1 micron range, we know that the virus actually attaches itself to respiratory droplets that are predominantly in the 1 to 10 micron range.
Right, and then again, from the energy perspective, here we're working with more pressure drop, essentially, right? We've got higher filters. As we move to higher filters, we're going to be looking at more fan energy. So we'll see from the results here that the impact of filtration is relatively minor, but still a consideration to take into account.
And then lastly, disabling demand control to provide the design or the increased ventilation rate within the space, and also disabling the energy recovery devices to eliminate any risk of cross-contamination of the return air with the outdoor air being delivered into the space.
From an energy perspective, these two are heavy hitters. By disabling demand control ventilation, right? Demand control ventilation is about providing the right amount of ventilation at the right time and not providing that ventilation to the same extent when there isn't an occupied condition. It's great from energy, right? But from a COVID mitigation perspective, thinking about additional outdoor air, more flushing, moving air to remove particles that we don't want, demand control ventilation becomes a little bit problematic. And so definitely a trade-off there. Similarly, for energy recovery ventilation, right? The concern around the contamination of those cross streams of air explains why it was recommended that be disabled. But again, from the energy perspective, right, we're not able to recycle and reuse preheated or pre-cooled air in buildings. And so the energy impact can be pretty meaningful for this one as well. So understanding those core recommendations, right, the benefits from the indoor air quality perspective, maybe the trade-offs with energy and carbon, we put this into our energy model, whether that was our spreadsheet or our simulation-based energy model, and crunch the numbers to see really what the impacts were overall for our 10 sample buildings. And what we found was that it can really vary. So if you look on the right side of your screen, you can see the range of impacts across those three metrics, energy, cost, and carbon, based on that core set of recommendations, right? 4% all the way to 43% on the annual energy increase. That's obviously a huge range, and you could even argue that 43% is an outlier, but it does represent a real building condition, right? A real building owner who's looking at the impact, or who was looking at the impact of these particular core recommendations to understand what the right next steps would be. From an average standpoint, the story is still pretty meaningful for these core recommendations, right? On average, that's the bar chart you see on the left here. You know, from an existing building condition, energy saw that average increase of 14% across all the projects, and then 10 and 11% on cost and carbon. Right, so these are meaningful increases. Certainly, it goes back to that original question: well, how much more energy am I going to use by following this guidance? And these are kind of the snapshot numbers from our sample set. Obviously, it'll change depending on which building you're working with, and can you hear me now? I was muted for a moment there.
Yeah, I can hear you now, Molly.
Okay, great.
It wasn't you, that was just me.
Oh yeah, no, we both went. I'm muted. In terms of high-level lessons learned, you know, I think we can kind of boil it down to these bullet points, right? Increasing outdoor air and then that faster dilution through the pre and post occupancy flush was certainly the primary driver of energy cost and carbon, right? We talked about the additional heating and cooling, the additional fan energy, of course. In terms of end uses, heating was the largest end use typically impacted. That's what we found across really all 10 of our sample buildings that participated in the study. I think an interesting one to note is that from a cost perspective, the upfront capital costs of core recommendations are relatively low, right? So if we think back to what those recommendations are, things like, you know, just kind of increasing your outdoor air through probably some BMS programming or some adjustments to dampers and controls, right? That's a relatively low upfront cost. But the real story is looking at that 10-year cost of ownership, right? We chose 10 years as opposed to 15 or 20, simply because some of the technologies, right, portable air filters, for example, you know, probably the 10-year time frame makes a little bit more sense. But yes, I mean, the main takeaway here is that initially it seems not very cost intensive to implement those core recommendations, but when you look in the long term, certainly those additional heating and cooling impacts stack up over time. Facilities with larger coil capacities and free cooling capabilities typically saw higher energy, carbon, and cost impacts. And that's because of what John mentioned before, right? The limiting factor for how much outdoor air you can really bring in are your infrastructure constraints and your coil capacity so that you can continue to provide a comfortable indoor environment, right? So if your coils and your infrastructure, your ductwork are large enough to accommodate significant increases in outdoor air year round, naturally there's going to be more of an energy cost and carbon impact. And then this final point, you know, facilities that have steam for cooling, that use, for example, an absorption chiller or something, or steam turbine chiller, because of the lower COPs associated with that equipment, the impacts from bringing in that more outdoor air are sort of compounded, right? You're already doing more heating and cooling, and you're doing more of that cooling, for example, at a lower COP. So from an energy perspective, those types of buildings would see a bigger hit. Okay, so moving on from there, it's sort of, we have to move on to the second question, right? The first question was, what are the energy costs and carbon impacts? The second question, if we think back to our sort of typical building owner, was, well, are there ways to optimize, to have improved indoor air quality, but also take into account energy and carbon and cost? And that leads us to our next slide here about, okay, the other recommendations that are out there and the other levers that we can pull to get better indoor air quality. So John, you want to go through a couple of these real quick?
Yeah, so in addition to the core recommendations by ASHRAE, right, we also evaluated the alternatives like UVC and portable air filtration. We combined the measures from the core and the alternatives to evaluate their impacts on energy, as you know, Molly will later talk about. But what about the emerging technologies? Right, these emerging technologies were not recommended by ASHRAE nor or other organizations, so we didn't evaluate them. Not to say that they're ineffective or not applicable to improving air quality. They just weren't evaluated due to the lack of the real-world application and their efficacy on improving indoor air quality.
Yeah, and to just sort of +1 reiterate that point, we wanted to focus this study on the recommendations that people were really most likely to proceed with or evaluate at a wider scale, right? And to John's point, the emerging tech is still kind of working its way into the industry, and the science around it is still evolving. it made sense to stick with the core recommendations and other well understood sort of widely applicable technologies. So to put this back into the context of our study, John mentioned stacking or combining different measures, and we essentially came up with 4 packages, I'll call them packages kind of moving on from this point forward, of different indoor air quality technologies that could be combined. And what we did was we evaluated them from an effective air change or equivalent air change rate perspective to try to get a similar level of effectiveness. And then again, we evaluated the energy costs and carbon impacts in our energy models to see if we're able to bring down those numbers from the core recommendations and still provide a good improvement to indoor air quality. So to sort of quickly go through some of these here, you know, for these different alternative packages that we came up with, we really focused on keeping with design outdoor air levels for systems that are currently in place, right? And then leveraging things like either an increased filtration going to a MERV 16, for example, in Alt1, or deploying something like portable filtration in particular areas in the building that, you know, maybe didn't have the best airflow or ventilation. And so through this process, we were able to come up with these different combinations of things to hopefully try to optimize both indoor air quality and energy. So similar to what we did before, we'll go through the energy cons, if you will, but the indoor air quality pros for each of these other technologies that we looked at in our packages.
So one of the alternatives that we looked at was the use of UVC. The system would either be installed in the air handling unit or the return air duct where space permitted, as you can see from this diagram. And also, and the system that we evaluated was we looked at a system that was 95% effective in activating the SARS-CoV virus in a flyby application, and that was equivalent to about 1,300 microjoules per centimeter square.
Great. And then, yeah, I mean, again, this technology we'll see in a minute here has a relatively minor energy impact, but right, obviously it's more plug load. You're putting something in that's essentially a lighting device. It's a high intensity lighting device specifically for this particular application, right? So some energy impact, but fairly minor as we'll see.
And then another mitigation strategy we looked at was the use of portable air filtration units in spaces where we had low air change rates. We considered implementing these to get an additional 2 to 6 air change rates. And this was, you know, we would use the effectiveness of the filter inside these in the air filtration units to deliver more clean air into the space.
So this one was a particularly interesting one for us from the energy side because there are just so many benefits. The fact that it's portable, right? You can really kind of put these anywhere. They have sort of a visual presence. So from an occupancy and perception perspective, you know, it's nice to walk into a conference room, for example, and see one of these little portable units. Kind of makes you feel comfortable, like, you know, definitely you're getting some benefit from indoor air quality improvement. But from the energy perspective, we found actually that to sort of, you know, really get to a point of equivalency with other technologies, you would have to deploy a fairly large quantity of these portable units, and the plug load impacts of that from the energy perspective can actually add up quite quickly depending on how many of these you need to deploy.
And then lastly, we considered the use of upper room UVGI, but we found that there was challenges in utilizing this technology, especially from a retrofit standpoint, because we were kind of unsure about the tolerance of UV in the spaces, especially with regards to the material that is in the space, and also exposure to the occupants within the space as well.
Yeah, this one we didn't even end up evaluating from an energy cost and carbon standpoint because we weren't really able to get over the initial feasibility hurdles that John just mentioned. Things like, you know, the finishes on the ceilings, for example, being important, or having concern around whether or not there would be an impact to those. Plus, again, that perception aspect of having a UV light in occupied space was something that, you know, we found was difficult for participating buildings to really kind of get on board with. So now to the findings, right? The good stuff here. And going back to that second question, are there ways to enhance indoor air quality without quite so much energy impact as those core early ASHRAE recommendations? And I think what we found, at least across our 10 buildings, is that yes, it is absolutely possible to optimize these two things. In terms of numbers, right, before we presented that 14% average increase to energy by going from the existing condition to the ASHRAE core set of recommendations from early April. Looking at our alternate packages that we just talked through, right, we were able to reduce that average impact, you know, down to 4% in certain scenarios, and really those coincided most closely with either using UV or taking advantage of a higher level of mechanical filtration in combination with design outdoor air values, or even slight increases, which we refer to as practical outdoor air increases. So maybe not going to that full capacity of your heating or cooling coil, but you know, some increase to indoor air quality, or I'm sorry, some increase to outdoor air in combination with other strategies. So I think this is really encouraging, right? You know, obviously the early core recommendations were a little bit on the conservative side, and as John mentioned, they've evolved and changed, I think, actually to align a little bit more closely with some of these 4% packages that we're referring to and we're able to evaluate. And 4% isn't nothing, right? But it certainly is, I think, a much better story than 14% or 10% or 12%. And so, you know, I think the high-level takeaways and lessons learned here, you know, number one, upgrading filter efficiency is a very effective strategy. And by doing so, you can really kind of minimize that energy cost and carbon impact, as long as you're meeting those code required, you know, design outdoor air values, or potentially bumping a little bit on the outdoor air if that's something that is desirable. Where filter improvements aren't possible, right? This is where I'm referring to this idea of a practical outdoor air bump, right? So maybe certain facilities aren't able to go to that next higher level of mechanical filtration. And so it could make sense to do some increase in outdoor air, just again, to get those benefits associated with moving air out of the space more quickly and diluting particles that maybe we don't want. In terms of flushing, not all flushing is created equal, right? You can flush to 3 outdoor air changes, right? Which is one of the ASHRAE recommended strategies. Or you could do a forced 2-hour flush. You know, obviously the forced 2-hour flush is more energy impactful. You can get to that 3 outdoor air changes most likely in significantly less time than 2 hours. And so, you know, in terms of strategies, that would potentially be the better one. In-unit UVC and portable air cleaners are effective strategies, certainly, especially when combined with things like design outdoor air or that minimum MERV 13 filtration. And I think, you know, areas where those make sense too are, as John mentioned, for the portable units, right? If you've got maybe poor circulation in an area, that's a really good opportunity to deploy that kind of technology. And then these last 2 points here, we mentioned upper room UV just being sort of a hard sell. But this last one, building owners have to consider maintenance requirements when selecting a strategy no matter what, because here we kind of presented the energy impacts and the opportunities to optimize for energy, right? But there are maintenance costs associated with some of those lower energy solutions. Take UV, for example, right? Shows a relatively minor energy impact, but, you know, you've got to install those systems in your units, and then in addition to that, there's annual maintenance required, bulb replacements, right, so on and so forth. And so something to consider there as well. All right, and then to close us out, we're coming to the end of our presentation here. I just want to kind of take a step back and boil it all down to a couple punchlines, right? So if you're kind of zoned out of the early part of this presentation, these are the high-level takeaways. You know, I'd say the first one John and I kind of found through this whole effort was that alternate strategies or combined strategies to improve indoor air quality while reducing energy impacts do exist, right? It's just a matter of finding the right solution for a building depending on its unique characteristics, but we can do it, so that's encouraging. Also, the world's understanding of COVID and how to mitigate it is obviously evolving. As Scott mentioned early on, the innovation in this area has been astounding. Obviously, ASHRAE and other organizations have been immensely helpful in helping building owners in the built environment understand what to do and how to move forward. And obviously, things will continue to evolve and change over time. So I just want to reiterate the point that our study focused on early ASHRAE recommendations, and that, you know, since that time, things certainly have evolved and changed, and will likely continue to do so. especially around the idea of emerging technologies, right? Hopefully in the future, there'll be more science to support some of those strategies and more consensus around whether or not they make sense for buildings in New York City and more widespread. This point, I think, is particularly important, the idea of a data-driven approach to indoor air quality, right? So deploying indoor air quality sensors and having some sort of occupant sort of awareness and participation and understanding of what's happening through the data, I think could really also be effective and beneficial. I think perception is certainly key to any good indoor air quality strategy. And when we're talking about the trade-offs and the optimizations between IAQ and energy, right, there may need to be some additional data-driven findings about whether or not a strategy is going to be effective enough to sort of justify the energy cost and carbon savings. So I really think this could change how things are perceived in the future. And then finally, the final point here, right? Each facility is different, and an evaluation of what's feasible and how to optimize between indoor air quality improvement and energy, right, should be considered by a professional, right? It makes sense to study this in every building and to approach every building a little bit differently, right? We've heard consistently throughout COVID, there's no silver bullet, and that's absolutely true. There's no silver bullet for mitigating the effects of COVID, and there's also no silver bullet for optimizing between indoor air quality and energy. So we have to approach it, sort of with fresh eyes every time, understanding the pros and cons of each technology, and then figuring out the right optimized solution for each individual building. And I will leave it at that. Anything to add, John?
No, I think you've covered it all, Molly.
Great. And that's it for us. I think we'll take any questions. Hopefully Scott will let us know if any come through.
Currently, no questions have come through.
Fair enough.
If anyone in the audience wants to post questions, you can post them in the chat as well, not just in the questions area, but also in the chat, as I mentioned to everybody. I have a couple questions, Molly and John. What happens when a building doesn't have enough airflow or doesn't have enough coil space? What really can they do besides putting air purifiers around the floor?
Well, I mean, if there wasn't enough, if the air handling unit isn't capable of providing the extra filtration or the extra airflow, I really, at this point, at least based on the recommendations that we evaluated, it really does come down to adding the portable air filtration units. Just because really the principle behind all this is trying to deliver clean air into the space, quote unquote clean air, just free of contaminants or particles. We talked about, we kind of touched upon the emerging technologies, but again, we're not, very strong on any of them, just because that there is a lack of, just scientific, results and just proven science as to the efficiency of those systems. So I think for the purpose of this, I would say we would try to stick with the portable air filtration units to get more air circulation and clean air delivery into the space.
Thank you, Jonathan. Also, I guess opening windows is an excellent strategy. I noticed that JB&B was instrumental in a New York Times article about increased ventilation in one of the major strategies, since most buildings have operable windows. But of course, what do we do in the winter time? If you're in a northeast area, is there any kind of air curtains or portable baseboard heating that can be implemented to allow windows to be opened? Do you have any comments on that?
Yeah, I mean, certainly, opening the windows when the weather permits, it certainly would be helpful. In terms, of, during the winter, or even, when it's really even in the heat of the summer, it can get uncomfortable within the space. And I think at that point, it's a little bit of managing the expectations of the occupants within the space in terms of what their thermal comfort levels are going to be. Air curtains is something that can be, I probably wouldn't recommend air curtains, just because the curtain that's going to be produced wouldn't allow the air circulation coming in from the outdoors, or at least prevent some of the air from coming in. But certainly putting in some sort of supplemental heat to offset some of the cold would be helpful. But obviously there would be other impacts on the energy usage as well.
Yes, absolutely. Energy impacts all around. Even with portables, we're actually working with a number of schools that only have window units, and therefore they're looking to go with portable air cleaners. Having portable air cleaners on floors can be a problem, especially with nursery schools and first to fourth grades. And also what is, of course, the energy impact of plugging in 60 portable air filtration units in each of the classrooms. Kevin Hunter sent in a very good and interesting question about what about direct UVC in elevators? And I assume that would be part of your emerging technologies.
Yeah, certainly. That's something that we can certainly, or that can be evaluated as well. Some of the concerns that we've come across is the safety concerns. Just making sure that the UVC system doesn't turn on when there are occupants within the space, right? And that system is only just focusing on the elevators itself, and really just the surface disinfection with regards to the buttons that the occupants coming in and out of the building would be susceptible to. But that is a strategy that is out there. Something else that we've looked into is actually just increasing the amount of air circulation within the elevator cabs, right? Upgrading the filtration at the elevator cabs and bringing in more outside air, and sort of building on the principle of diluting the concentration of particles within the elevator cabs as the occupants are occupying the cabs.
Nice. A lot of elevators I've gone in when I do building surveys, they have a plastic coating on them taped on top of the buttons, and therefore the maintenance and janitorial staffs can constantly go in there and wipe them down without ruining the actual buttons themselves. I guess that's a very, another simple strategy that's been implemented. James No asked, did you track particulate reduction in the occupied spaces during your testing phase?
No, we didn't. So this was all primarily I'll say a theoretical study, right? So we went out and evaluated the existing systems, and then evaluated energy cost and carbon impacts through our energy models, right, which are simulation-based evaluations. I think we would love to take the next step and install some of these recommendations, and then do a measurement and verification exercise to actually determine what the true data-driven improvements to indoor air quality would be, but it wasn't part of this particular study at this time.
I understand. Please forgive me if I don't say your name properly, but Zgang Zhu asked, any ASHRAE code changes due to COVID-19? Actual changes, whether it's ASHRAE or New York City? Any code changes that you are aware of?
Not that they were aware of. Obviously, some of the things that were studied obviously has an impact on energy, but so far we don't expect the energy code to change due to COVID.
Yes, we just got a follow-up comment from Kevin Hunter, who asked about the direct UV in elevators, that occupancy sensors are what's used there to control any type of exposure. My concern, of course, would be if the occupancy sensor fails. And we have a lot of ultraviolet light systems in clean rooms for different kinds of production of cancer medicines and research. And we regularly validate those motion sensors. And every now and then we find a sensor that doesn't work and does fail. We have door switches and other things for safety, but the motion sensors need to be, there's a bit of a liability there anytime you need a motion sensor to safeguard any type of technology, especially if it's emerging technology. It's one thing if ASHRAE or CDC or the WHO has done the research and therefore there's a lot of understanding of the technology. In the emerging technologies, we need to have an additional level of caution, I'm sure we would agree. Marwa Zatari asked, did you consider design occupancy or reduced occupancy when you considered the design outside air? As we know, most of the spaces going forward will continue to be socially distanced, and therefore occupancy rates should go down.
Yeah, that's a great question. So part of this study did evaluate all of these impacts in a fully occupied condition, and that was intentional. To sort of see, okay, what are we working with, or what are going to be the impacts when people do reoccupy buildings? Now, I totally agree that moving forward, it feels unlikely that we'll get back to 100% occupancy. Now that there's going to be social distancing, and then potentially flexible work weeks, right, where maybe there's certain numbers of people in on certain days and working from home on other days. So it's entirely possible that the energy impacts of those early recommendations would be less than what we're projecting if that, a partially occupied condition were to actually be the future condition. But we wanted to look at the worst case, I guess is kind of what I'm saying here, is we wanted to evaluate what it would look like if things went back to quote unquote normal from the energy cost and carbon standpoint.
Absolutely. I think it'd be interesting for facilities that are having a struggle with determining which strategies or technologies to implement because their equipment is undersized, to consider their occupancy rates as they go through the process. If they do reduce, there could be some ventilation effectiveness and strategies that could be implemented well. A very interesting question that I got was, could you explain the flushing sequence and with the understanding that a person walks into a room who hasn't been in that room, let's say it's a classroom, there's been a class in session with the teacher and the 8 or 12 students, and all of a sudden someone comes into the room. Are there additional strategies to reflush the air?
Interesting question. Let's see, John, do you want to just take the question on the flushing procedure and what it's about, and then maybe I can opine on the second part of the question there, just about different ways to do the flush?
Yeah, sure. So the idea behind the flushing is that before and after occupancy is that to try to get rid of any of the particulates that may have been generated within the space while people have, while the space has been occupied, right? And try to essentially deliver a clean space for the next group of occupancy or the next time the space is occupied. With regards to trying to, I guess, treating the air or trying to filter the air while the space is occupied, right? That kind of goes in line with the delivering the air change, equivalent air change within the space while the space is occupied. So it kind of like two different strategies, if you will.
Yeah, and then I guess to sort of add to that, the flushing that we evaluated was the type of scenario in which you've got typical operating hours, right? Typical normally occupied operating hours. Let's say for the sake of argument, it's 9 to 5. then you would be doing a flush before 9 a.m. and you would be doing a flush again after 5 p.m., right? So in the case that you're posing here, Scott, with a school where you're sort of going from an occupied classroom to a break where it's an unoccupied classroom to an occupied classroom, so on and so forth, you know, I imagine from a controls perspective, you probably could enable a flush in between that first class and that second class if there's a period of time in which that room is empty. And just depending on, you know, the characteristics, the fan characteristics of your system, the number of minutes to achieve that 3 outdoor air changes can vary, right? So, you know, potentially you adjust your system to accommodate that 3 outdoor air changes in the period of time between those 2 classes in which the room is unoccupied. That could be a strategy. It's not something we directly evaluated as part of what we did here. But, you know, it certainly seems doable.
Yes. One of the things that I've come in many questions my clients have asked me is with the portable units, they're loud. And actually someone made the comment, portable units are very loud. What I see in many of the portable units out there is that on low or on low medium, let's say they have 5 or 6 speeds, on speeds 1, 2, and 3, the dB levels are around 40 to 45 dB, and they're very reasonable inside of rooms. And when you put them on that 4th, 5th, or 6th gear, that's when they become very loud, mainly because of the airspeed and the force that it takes to get through the filtration, whether it's HEPA or something of a MERV 13 or MERV 14 equivalent. And one of the things that I've recommended to, especially for schools, is that when they go on that break and the room becomes unoccupied, they turn the unit to its high level. And then when the teacher comes in to check the class before the students come in, the children come in, they again turn it back down to the level that would be reasonable to still teach without the sound problem. And I've noticed that some of the units out there have Wi-Fi capability. Have you seen that kind of Wi-Fi Apple on your phone control with some of these technologies in your research?
We've seen a lot of the portable air filtration units with the Wi-Fi capabilities, more at the consumer level. You know, if you're looking for something more like a heftier, you know, HEPA filters, those sort of, you know, I guess options aren't as readily available. But Scott, I guess kind of what you mentioned is sort of mimicking that post and pre-flush sort of strategy that we're talking about, right? Is really trying to get as much of the air, you know, passing through the portable air filtration unit between occupancies, right? As kids enter and leave the classroom, right?
Right. Yeah, that's exactly what I was getting at. Is, you know, what kind of easy strategies for most facilities, especially if you put museums, theaters, restaurants that have had a very difficult time financially through 2020 and the pandemic because of lockdowns. They are on shoestring budgets and they have limited capabilities. So even simple solutions like opening windows can really go a long way at mitigating the risk, at lowering the viral loads in the spaces. Another question that was asked by one of our panelists, and I wanted to make sure to ask both of you this for your opinion. It's a raging debate all over my LinkedIn page because I'm in strictly focused on indoor air quality and the control of infectious diseases. Is those emerging technologies? It's pretty well known that the core recommendation is MERV 13 or higher from a technology standpoint. And then the next technology that's accepted by ASHRAE and CDC is UV, as you spoke about. But bipolar ionization has become extremely widespread utilized in many schools around the country. And Did you, even though it was an emerging technology, did you evaluate that as part of the research, or are there any plans to look at those emerging technologies in the same light that you looked at MERV 13 and the other strategies that you did discuss?
So I'll answer the first part of that question there. We did not evaluate them as part of this research project, and that was intentional because of the debate around bipolar. Again, to go back to sort of our earlier slide, we wanted to evaluate the things that are sort of well understood, widely accepted, recommended by the agencies that are providing this guidance for safe reopening. And so we didn't evaluate the energy cost and carbon impacts. However, that being said, and John can kind of speak to this a little bit more too, you know, just as a trusted advisor to our clients, we're familiar with that technology and have been asked certainly to evaluate it from a feasibility and a cost perspective. We just didn't include it in this particular study for the reasons that I mentioned before.
Yeah, and knowing that it's an emerging technology and the science is still kind of coming out, and additional research is done, and you know there's been recent research as well as you know with regards to the effectiveness and any sort of byproducts that may be produced. I mean, it's something that we're keeping a pulse on, but at this time it's not something that is because it's not one of the core sort of recommendations. You know, we haven't kind of evaluated from an energy standpoint, but it's certainly something that we're keeping track of and once you know, trying to stay up to date on in terms of the science that comes out of it.
Absolutely. I think we all understand that it's very important to follow the science, to follow the guidelines, core recommendations that ASHRAE has set, especially now that across the HVAC in our industry and even the world in general, ASHRAE really has developed a very prominent role, as I mentioned in the introduction, as an expert panel of experts. And I believe there's well over 100 scientists and well-established experts in indoor air quality on the Epidemic Task Force, working on numerous groups. One of those being flushing technologies, another one being emerging technologies, another one being safe distancing. And there's a lot of different groups. I would deplore everybody on the in the audience to get on the COVID-19 ASHRAE website and research all the resources that are out there and all the individuals that are volunteering and working tirelessly in this effort. So thank you so much, Molly, and thank you so much, John, for preparing the presentation and being available for all the questions. I'm just going to scroll down and see if we had any last-minute questions. I think Marwa actually asked for a further explanation of, did you take a look at the first cost of these different solutions? And if you could talk just for a moment on that.
Yes, we did in fact look at first costs in addition to that 10-year cost of ownership. And it's important to understand the distinction between the two, because certain solutions, as I mentioned in the presentation, have low upfront costs, things that are primarily controls related, right? So making an adjustment to an existing BMS program through, you know, most likely a service contract that already exists has a relatively low upfront cost. But in the long term, right, making that change to go to, let's say, a much higher level of outdoor air year round, the utility cost impacts, right, the operations and maintenance cost impacts really outweigh that initial cost. And so it's important to look at both. You know, while the core recommendations, controls related strategies had lower upfront costs, generally speaking, you know, things like the portable units, UV, right, some of these technology-based solutions obviously had much higher initial costs, but in the long-term 10-year cost of ownership perspective, were significantly less expensive than some of those sort of sneaky controls related items that feel like they're not very expensive. So yes, absolutely looked at both. I don't remember the exact numbers off the top of my head right now, but it's a little bit of a different story than you would anticipate, right? You really have to look at that long term and what's going to be the total investment that a building is going to make in something, you know, and factor that into the decision-making process.
Absolutely. The first cost, especially with a lot of CARES Act money available, that can be mitigated in some instances, especially for schools. But the schools and other facilities will be obviously left with any kind of operating costs or maintenance costs. It'd be great to just shove HEPA filters into every filter slot. And even if you had enough energy and enough capacity in the AC unit to handle the increased static, because the HEPA would obviously grab and collect so much more dirt, which would be a positive, it would also require changing more often. And it being roughly 10 to 20 times the cost of a standard 2-inch pleat, that could be an extremely expensive endeavor for any school or museum or a facility that's sometimes they are publicly funded or government funded. So without any further questions, once again, the audience and everyone we have one more question. We might want to reiterate for the audience that, so that this is the age of COVID. So we're confronting a long-term operating environment and its costs, not just a momentary crisis that will pass into history. I've said to a lot of my clients that you're not just implementing these strategies, many of the ones that Molly and John just talked about, simply for COVID. That there's been a pandemic that's been raging in our country and around the world for 30 years now. We call it the flu. 20 to 50,000 Americans die on average every year. Over 1 million people on average die around the world. And some of those are from other influences, third world conditions and such. But many of them are for the same reasons why we are finding COVID-19 so difficult to control, is that it is not just a surface-related contact issue. It is absolutely an airborne problem. And therefore, many of these strategies going forward will allow us to provide just generally better health and a better environmental environment to the customers, to the clients, to the end users of these buildings. And I know it's that's really the goal of JB&B and all of the mechanical engineering firms that are not just part of this panel, but part of the industry. It's not always just about the bottom line, but it's really about the environment that we're designing for the people that occupy these spaces. So that said, thank you so much for the preparation and the excellent presentation. And we are now going to take a 10-minute break. It is 10:10, and we will come back at 10:20 to begin seminar 2, which will be given by Bill Bahnfleth, who is the chair of ASHRAE's Epidemic Task Force. And we will see everybody at 10:20 a.m. sharp. Thank you very much.
Thanks for having us.
So this would be a good time. of the audience ask as many questions as possible to spur the discussion. A question from last year's conference, we should have asked Molly and John this. It was an interesting question that will carbon emission policies like Local Law 97 fade in the wake of the pandemic, and how buildings are going to be expected to be designed in the future. So what is that, the nexus of Local Law 97? We might get some of that information in the third presentation when we talk about electrification and how to move away from the direct burning of fossil fuels for energy in buildings, which is a very interesting topic. For last year's first annual event, it was directly after the pandemic started. And we decided not only to delay it until, I believe, the end of May, but to focus it specifically on the pandemic. And that's why we had invited Stephanie Taylor, who is an expert in indoor air quality. She is part of the Epidemic Task Force. And her focus has always been on the importance of relative humidity control. Between 40% and 60% relative humidity has shown a great capability to reduce the viral load and increase the indoor air quality dramatically. And once again, like Molly and John spoke about, increasing relative humidity does increase the actual load for air conditioning of the space. So it needs to be considered from not only a first cost, but from an operating cost. But for this year, we wanted to, since it is an Earth Day event, we wanted to focus and refocus the discussion also on the energy, on the sustainable side of this discussion. How do we get to net zero? How do we reduce our dependence on fossil fuels and methods of energy capability that take our environment out of balance? We really do need to focus on how we get back into balance with the environment. Many cities across America have already developed strategies for more flooding, the inundation of high winds and damage during increased levels of storms, tornadoes, hailstorms. The list is endless of the, let's call it, extreme weather conditions that we've seen. I don't think anything is as blatantly illustrated as in what happened in Texas recently, where it was snowing and colder in Texas than most of North America, and the damage caused was just dramatic. You could say it was one of preparation, that the state wasn't well prepared. The amount of natural gas facilities that had to flare off methane gas was remarkable. It was a historic level of how much was flared during those 3 or 4 days. And those are the strategies that we really need to end. So we are honing in on 10:30, and I am going to introduce Bill Bahnfleth, who is a distinguished lecturer and ex-president of ASHRAE. He is affiliated with Pennsylvania State University, but most important, he is the chair of the Epidemic Task Force, and he has spoken to numerous government, state, local, and federal agencies, along with CDC and just about everybody that is interested in airborne infectious diseases. So I am going to turn over the screen over to Bill. Bill, can you hear me?
Yes, I can, Scott. Can you hear me?
Yes, and I can see your screen. So it is 10:27. Let's wait a couple more minutes just in case someone who expected your presentation to start at 10:30. What do you think about adding plants and or any other ideas to a space to help the process of increasing air quality?
Oh, well, plants have been discussed as the natural kind of air cleaner for a while, and I'm not convinced that they're a substitute for the other sorts of things we do to improve air quality. I think my view of indoor plants is a little bit like Joe Stebrook's view of green roofs. If you like grass on your roof, then do it. But if you want to have more insulation in your roof, then just put more insulation in it. I think plants indoors are nice, and maybe they do some good things, but I wouldn't rely on them. And they do bring other issues with them. If you have a lot of plants, they transpire a lot of moisture, and they're also in many cases in soil, and soil can have microorganisms in it. So I haven't studied it closely, but I don't see it as a big new tool for IAQ. If people are interested in that, I believe Michael Waring at Drexel actually published a paper on that within the last couple of years, and found the evidence for its effectiveness to be somewhat limited. That's sort of where I sit with it. I'm not looking to the day when it will be in the ASHRAE COVID recommendations.
Oh, great, thank you. And we'll ask that same question to the panelists during the panelist forum. A lot of these questions, the ones that Molly answered, the ones that Bill will answer, and Jeffrey for electrification, we will go over these questions to get different perspectives from the 5 panelists that we have from 5 major mechanical engineering firms here in New York City. So it is 10:30, almost 10:30. And I am going to turn the screen over completely and mute myself for Bill to begin his presentation. Thank you, Bill.
Okay, thank you, Scott. And I believe we're all set now with the technology. I appreciate the invitation to come back. Some may not remember, but I spoke at this program a year ago, and it was actually my first canceled live presentation of the pandemic. So it's been a year since I gave my first virtual COVID-related talk, and at that time, what I was doing was presenting the very recently released ASHRAE infectious aerosols position document, which replaced the position document called Airborne Infectious Diseases, which I'd been talking about as an ASHRAE lecture topic for a number of years. And at that time, we had only had an epidemic task force for a few weeks, and it hadn't produced any guidance. And in that vacuum, the infectious aerosols position document essentially was ASHRAE's guidance. And I would say now that it has been, to a large extent, superseded, in some cases contradicted in terms of its specific recommendations about what to do. And I want to emphasize that everyone should focus on what ASHRAE has actually got up on its website now. And what I'm presenting here today that's been one of the challenges of the past year, is to keep everyone on the same page as we have dynamically changing guidance. So what I'm going to do today is discuss these and present the core recommendations that were mentioned many times in the first presentation. And also I want to talk about another important section of ASHRAE's guidance that's at the website, which is the building readiness section, which is about implementing these recommendations. And when I talked last year, I gave a lot of background on airborne infection transmission, and we can skip over all of that now. I think everyone has heard enough that airborne transmission is considered to be a significant source of risk for us when we're indoors. Both WHO and CDC are now acknowledging that, although perhaps not as strongly as some would like. But I think we can simply move beyond that to saying that we need to have guidance for how to control risk of airborne infection in buildings. So we'll start with these core recommendations, and note that they were actually approved by the task force on January 6th of this year. So we were applying in the previous presentation this term core recommendations retrospectively to whatever we were doing at the time. But in fact, what we call core recommendations now were something that developed towards the end of last year after the task force had been producing guidance for a while. And what they are is the most concise summary that we could produce of the framework for the several hundred pages of guidance that you'll find at the ASHRAE website, and with two purposes in mind. One was that, as Scott noted, we had well over 100 people working on 15 teams to develop guidance, and we needed this list of things we were trying to implement in different contexts to keep everyone within the task force on the same page. Some contradictions were starting to crop up between different types of buildings because different groups were working on them. And the outward facing purpose was communication. It's hard to get the public to look through several hundred pages of guidance, and then even harder for them to get a sense of what the principles are behind it from looking at all of that detail. So communicating these basic ideas was one of the central goals, and also to address the issue of changing guidance over time to document what the current status is. So the hope was that by making this statement of the basic principles we were applying, that it would help to stop the public and the professional community from trying to implement things that we had moved beyond, in some cases, many months before. I still see the infectious aerosols position document cited as ASHRAE's guidance, and different groups using those recommendations, which in some cases are really kind of harmful from the point of view of cost and energy use perspectives. But it was justified at the time. If you think back to the beginning of the pandemic, we were all pretty worried and perhaps even scared about what might happen. And everyone was in a frame of mind to take the most extreme measures achievable to try to reduce risk. The other thing I want to say before I move on is that these recommendations embody the flexible approach to meeting risk reduction targets that was discussed in the first presentation. So with that, let's go through them briefly. The first recommendation relates to public health guidance and simply says that you should follow it. We do not want to give the impression that because engineering controls are being used to reduce airborne transmission risk, that means that all the good public health guidance that is available no longer needs to be followed, and that especially refers to things like distancing and the use of masks. One reason for doing that is that we know that there are multiple modes of transmission, although exactly how heavily weighted each one should be, we don't know for sure, but airborne controls can't take care of everything. And another important reason from ASHRAE's point of view to follow recommendations to use masks is that the use of masks reduces the amount of infectious aerosol put into the air by an infected person. Even a surgical mask that's reasonably well fitted could remove 40 or 50% of the infectious load that someone might emit if they weren't wearing a mask. And as you can see in the images in this slide, a mask also can stop these longer range, high concentration, large droplet aerosol emissions that happen with coughs and sneezes by blocking them. So you see the very widely disseminated Lydia Buruiba image of a sneeze moving 25 feet in the upper figure, and in the lower one, someone wearing a mask, and you can see the extent to which the jet that they would have been creating by talking has been mitigated by wearing a mask. So that's important. But now we get into the things that have to do with HVAC systems, and the key area is ventilation, filtration, and air cleaning, starting with outdoor air. And the recommendation here is that systems should at least bring in the minimum outdoor air that's required by code or standard applicable where the building resides. And this is a recommendation that in one perspective counters the initial recommendation that ASHRAE and others made that we should increase outdoor air as much as possible. That's very energy intensive and expensive, as has already been discussed. And so we came to question whether it was actually necessary if we could define a target for risk reduction. And so that's what you see as we go forward, that we now are of the opinion that other controls can be as effective as increased ventilation without adding to the energy cost as significantly, and also without compromising comfort, which is potentially a problem as well. But it's important to note here that minimum outdoor air, even with MERV 13 filters added, is not necessarily sufficient to achieve acceptable risk reduction. That requires some analysis, and we'll talk more about that in a little bit. With respect to filtration, the recommendation to use MERV 13 or better in recirculating air streams stands, but you'll notice that this recommendation says use combinations of filters and air cleaners that achieve MERV 13 or better. So this puts some wiggle room in there for the central systems or other components that are not upgradable to MERV 13 for whatever reason. You know, Marwa Satari is on and has talked a lot about how this is not as much of a problem as many believe, but it can be an issue. And now we have a recommendation that allows the combination of UV with a lower efficiency filter to achieve that level of performance, or to have two filters in series, for example, two MERV 11 filters to get to a similar level of performance. And just to reiterate why MERV 13 filters are recommended, if we look at the spectrum of size of respiratory emissions, most of the droplets that are likely to travel very far and contain viruses are in the roughly 0.5 to 5 micron range. If we consider the three rating size ranges for MERV filters established in ASHRAE standard 52.2, we see that for MERV 8, which is currently the minimum in ASHRAE standard 62.1, that there's no minimum efficiency required for 0.3 to 1 micron particles, and only 20% for 1 to 3. So that covers the peak in the distribution here. And if we go up to MERV 13, the minimums are now 50% and 85% in those two ranges, and they will perform much better in terms of removing particle sizes that are likely to contain infectious material. With respect to air cleaners, we have a very concise, terse statement here that only air cleaners should be used for which evidence of effectiveness and safety is clear, and this has already been touched on. some technologies are emerging, some technologies aren't really emerging. They just haven't, over decades of being available, done what's necessary to establish that they're safe and effective, and that's a concern. There have been huge sales of a lot of products that don't have a very strong evidence basis in peer-reviewed research. The only technology that ASHRAE feels has a sufficiently strong record of performance that we can say with some confidence that it's been shown to reduce risk of airborne infection is UV. And this is not something new. That was a statement that was made in the original Airborne Infectious Diseases Position document in 2009, based on a very long record of research on that technology. So until these issues are resolved with some of the other technologies, and I hope a number of them prove to be safe and effective, we need to be very cautious about using them. Fortunately, there's been quite a bit of publication in recent times on these, and I have an image there of one of the recent independent studies that was done by a manufacturer that looks at bipolar ionization, and the same manufacturer has also done studies of other air cleaning technologies as well that they're in the process of publishing. And the next sub-item under ventilation, filtration, and air cleaning deals with the combination of controls. So select control options, including standalone filters and air cleaners that provide desired exposure reduction while minimizing associated energy penalties. This is important because it recognizes the applicability of this approach of equivalent uncontaminated air supply that allows us to some extent, mix and match between ventilation and filtration and air cleaning. The biggest problem that we have with implementing this right now is that we don't have very extensive information on what those total uncontaminated air supply quantities should be, and that's something that the task force has been working on for a while now, and it's a difficult issue, and we're hoping to get recommendations out quite soon, but still have some discussion that needs to take place before we can do that. This recommendation again enables taking an approach like the one that was demonstrated in the first presentation to combine controls in a way that is aware of energy use and cost factors while still creating a sufficiently safe environment. And this has been done largely on the basis of airborne infection risk analysis with the Wells-Riley model. The Wells-Riley model, for those who have been paying attention to discussions of it in the last few months, is an imperfect tool, but it's about the best one that we have. It relates risk of infection to the emission rate of infectious materials, number of infectors, and the rate at which they're emitting infectious doses, and the dose that's inhaled by someone who's susceptible. So that's a function of their breathing rate and the time that they spend exposed to contaminated air, and also related to the uncontaminated airflow rate. So the first two factors increase risk if they get larger, and if uncontaminated air supply to dilute the infectious source increases, that will reduce risk. And so if we establish a risk criterion and we know the conditions that apply to that scenario, then we can calculate an uncontaminated airflow, and then we can generalize the idea of uncontaminated airflow to include clean air produced by filters or air cleaners. So we have infectious quanta or infectious dose production estimates for COVID-19, but they're not highly accurate, as you can see from this figure that shows that indeed there is a significant difference in production rates for different respiratory activities. This is about a couple of orders of magnitude across the different activities, but also within any activity like breathing or speaking loudly, there's 2 orders of magnitude between the 5th percentile and the 95th percentile. So there's a lot of uncertainty here. We can use this kind of analysis to come up with strategies for controls and also for occupancy. So the Skagit Valley Choir practice was one of the early super spreading events that led to the conclusion that there was airborne transmission. A couple of figures from a paper analyzing that event are shown here. And the left, we see that the probability of infection as a function of the equivalent air change rate. This loss rate coefficient is in units of air changes per hour. And in this plot, we see the effect of different emission rates, which has a significant impact. So suppose that we had 6 air changes, the difference between 550 quanta per hour and 1510 quanta is a doubling of infection risk. And on the other side, what we see is the impact of duration of occupancy from a half hour to 2.5 hours. And again, that has a big impact. So this has been used extensively to develop recommendations, and it's the kind of thinking that we're applying in trying to develop ASHRAE recommendations on clean air supply requirements. And so as I said earlier, we can put the Wells-Riley equation in terms of total air changes that accounts for both outdoor air and air cleaners. And if we have a target, then we can sum up all of the different removal or inactivation mechanisms to meet that target. So that's the ventilation, filtration, and air cleaning recommendations. Now on to air distribution, which we didn't pay a lot of attention to initially because most buildings don't have a lot of capability in a short term to change air distribution, but we're increasingly realizing that it's important. And so our guidance here is that where directional airflow isn't specifically required or recommended based on having done a risk assessment, low velocity mixing in spaces tends to create the lowest overall risk because it's dispersing infectious aerosol more uniformly and resulting in the time to have an exposure to an infectious dose being longer. One reason that we make that recommendation is that stratified ventilation has been shown in some cases to trap aerosols in the breathing zone and increase risk rather than, as we might expect, reducing exposure, because that's what happens with a lot of other contaminants. The other reason for this guidance is to underscore that strong drafts in the breathing zone can move even large droplets long distances and cause infections. So to those 2 points, on the right in this figure, we see some flow visualization that was done in a study of stratified air distribution in healthcare facilities, and you have a mannequin creating visible plume. And you can see here that under the conditions in this space, it's hanging in the air where others could breathe it for a long time. On the left, we see a figure from a recent case study of a COVID outbreak in a restaurant in South Korea, and there was one infector who infected 3 people, their dining partner, and 2 others who were at quite a distance away, 6 or 7 meters. And the analysis of this event suggested strongly that the main factor here was high velocity air motion from where the infected person was to where the susceptible people were. We have a couple of ceiling cassettes, VRFs, that are creating a velocity along this axis of over a meter per second, about 10 times what we would expect to be a normal air velocity in a typical mixing ventilation system. The reason that this is the most likely cause of infection, is that they had cell phone records for all of these people, and A and B were only together in the restaurant for 5 minutes, and C and B were there for 20 minutes together, and no one else was infected except for the person right across from them. So I expect that we'll see more development of guidance on air distribution, perhaps some modifications to the recommendations as a result of that. We have a sub-team working on that right now. The fourth recommendation deals with humidity and temperature control, and our recommendation continues to be maintain temperature and humidity design set points. This is walking the line between recognizing that there are benefits to humidification, which ASHRAE has said for a long time. If you look at the humidifier chapter, I think it's 22 in the applications handbook, you'll find that since the 1980s, ASHRAE has suggested that humidity ought to be between 30 and 60%. But on the other hand, if buildings aren't humidified, the cost of putting in humidification systems can be quite high, as some of the case studies in the program that was discussed in the earlier talk demonstrates. And also it can be harmful to some buildings if their envelopes are not up to humidification to 40% in a cold climate. The other reason that we have this not very strong recommendation is that it's not clear that relative to COVID-19, humidification makes a huge difference in terms of reducing overall risk. There are certainly studies that show over time in a healthcare environment that higher humidity, or at least not having really low humidity, is associated with lower disease incidence. Haven't really seen that with respect to a highly contagious epidemic disease like COVID. And on the right here, we have some influenza data by Lindsay Marr from Virginia Tech, and she studied the effective relative humidity on the active life of influenza virus, and indeed there is a big effect, as you can see in the inactivation data that I'm showing here. This goes from 10% to 90%, but the removal rate by ventilation, even at 1 air change per hour, is pretty comparable to the inactivation by humidity, and settling is a larger impact than inactivation. And so when you add together all of the removal mechanisms, we don't see a very big impact on the total by humidity, even at 1 air change. And if we go to 10 air changes, in the other example, this removal rate is practically unaffected by humidity. So that's why we're saying this. But if you have humidification, that's good. Keep your system working, and if you really want to add it, do it, but it may not be the most impactful measure you can take to reduce risk. And so now we move to a group of recommendations that are lumped together under system operations. The first is to maintain equivalent clean air supply for design occupancy levels whenever anyone is in the space. Why do we say this? It's important because it discourages the use of demand-controlled ventilation, reducing ventilation in proportion to the number of occupants, which would increase risk of infection according to the risk model we just looked at. And it also underscores the need to protect anyone who's in the building. So that includes maintenance and janitorial crews. So even after hours, in the terms we might use, buildings should be ventilated when there are people there. And now flushing. Flushing between occupancies was something that in the early guidance was a fairly conservative recommendation. Do it for a couple of hours before and after occupancy. And Actually, at the same time that we were talking about that, we were still at a time when 24/7 operation of systems was being recommended by many. So this recommendation is moving to a position that we don't need to operate systems all the time, as long as we're ensuring that we are clearing the air when necessary. And we don't even need to flush before and after occupancy, because it's really between occupancy periods that matters. 3 air changes has been discussed as a flushing amount, because that, according to a well-mixed space model, will result in 95% reduction in the initial concentration. If we want to get to 99% clearance, it takes 5 air changes. And this can be accomplished on the basis of the total equivalent uncontaminated air supply. It doesn't have to be outdoor air. It can be, again, outdoor air plus filtered air plus treated air. I'll say more about that in the second part of the presentation here. There is also guidance on preventing reentry. The main concern initially was that we might have recirculation through energy recovery devices, but there are other opportunities for that as well. What the guidance says now is limit reentry of contaminated air to acceptable levels. The original recommendation, as you may recall, was just to shut ERVs off because they might be sources of recirculation. That's been rethought, and guidance has been developed on how to determine when it's actually a risk, so that in most cases ERVs can be safely operated. Other opportunities for reentry include plumbing and ventilation shafts, and there have been some recent incidents that demonstrate that. For example, a South Korean apartment building where there was a cluster of cases that were vertically aligned on the same plumbing shaft, and it was the same thing that was found during the original SARS outbreak, that there was an infected person in one apartment, and fecal aerosol was produced in the plumbing system, and there were other apartments that had dry traps, and so air could re-enter. A similar kind of thing happened in another apartment in building in South Korea that was documented. These were infections that were vertically aligned in units that were connected to natural ventilation shafts. So these shafts ran the height of the building. They were open. There were no dampers to prevent backflow into apartments. And so given stack and wind pressures, it was possible for infectious air to enter the shaft from one place and go into another apartment due to stack pressure or wind pressure effects. And the final core recommendation has to do with commissioning. Verify that HVAC systems are functioning as designed. And everyone understands that we have serious issues, not just in the US, but around the world, with how HVAC systems are maintained. And if they're not operating properly, then we really can't say very reliably how well they're going to perform during the pandemic if we try to update them. One of the recent studies that has been widely circulated is the GAO report on the condition of US schools, and found that 1/3 of HVAC systems in schools in the US need repair or replacement, or stated another way, that 41% of school districts have 50% or more of their HVAC systems in need of repair or replacement. So this is very important for risk reduction, but also we have a lot of history looking at the effects of retro commissioning that suggest that if we have buildings functioning as they were designed, they will use substantially less energy than they would if they're in a degraded operating condition. So this is important both from the point of view of air quality and sustainability. So those are the core recommendations as they sit today. They may change, but they embody, I think, a fairly well thought through set of guidelines, and now I want to spend the rest of the talk here on building readiness guidance, which is a section of ASHRAE guidance on implementing the core recommendations. So in overview, it addresses planning, assessment, implementation, and reopening, and combines the infection control guidance we've looked at with some concepts from commissioning. You can find that at the ASHRAE.org/COVID-19 page. So this is the top page of the guidance, and you can see it's mainly divided into 3 sections: general information, epidemic conditions in place, and post-epidemic conditions in place, which deal in the first case with mostly with planning, and the second with specific measures for the pandemic and their implementation, and in the third with going back to normal operations after an epidemic or pandemic is over. So the 3 main things in general information are a section on intent, what is this guidance for, another section on the team, who should be on the building readiness team that does the assessment and implementation, and also the plan, how should we document what needs to be done to update a building. So who should be on the team? Consistent with commissioning and then also with infection control guidance, it should be a team with broad qualifications. So someone who's a commissioning provider, someone who can do test and balance, someone who's knowledgeable in building automation systems, contractors, architects, operations staff, and owner representatives to get all of the perspectives. The building readiness plan that's described in this section of guidance provides a record of mitigation strategies, both HVAC and non-HVAC, that should be implemented. Examples of the non-HVAC strategies are shown there, that include occupancy limits, distancing, circulation patterns, and others. It's important to include these because to get the appropriate overall level of risk control, we need to do all of these things. We may have seen the recent statements that schools could go to 3-foot distancing that CDC has put out. And yes, that's possible, but you need to read the technical brief that goes along with that, that says that assumes that everyone is wearing masks and that HVAC and other protections have been put in place. So there's a presumption that we're doing all of the things that are part of a good risk management plan when we change our HVAC system. We've already talked about the HVAC strategies. This should be addressed for every system, not just generically. I think that's an important point that comes out of the first presentation, which is, while it's great to have some general guidelines, they do have to be adapted to each particular building. So what we're talking about here is the Swiss cheese model of infection control, which is perhaps a little more engaging way of putting it than the hierarchy of controls, but it's really the same thing. We've had many discussions over the past year of the hierarchy of controls, elimination, engineering controls, administrative controls, PPE, where what we're doing with HVAC is here in the engineering controls realm. Think of each of those as a piece of Swiss cheese with holes in different places in it. So if we put enough of those pieces together, there's no path from one side to the other of our stack of cheese slices. Right, so in the building readiness plan that's developed by that team, a number of operating modes are considered, and they're all listed here. We won't discuss them in detail, but this points out that we should think about the different modes in which a building operates, again, going from general principles to something that's specific to this facility, from occupied at full or reduced levels to temporarily or long-term unoccupied, and then getting back to normal operating modes when we return to full post-pandemic occupancy of a building. So what's the process? It's not unlike commissioning or retro commissioning. Get information, evaluate the systems in person, go there and look at them, see what they're doing, identify the maintenance issues, identify the mitigation strategies that ought to be applied, and from that, create a work plan, work orders, and then review it and get approval from the stakeholders and implement it. The graphic on the right here shows the many specific sections in building readiness that deal with particular mitigation strategies that might be implemented. So the key topics, I think, from that list are the evaluation of systems and ventilation increases and filter upgrades, which have been talked about already in the case study, application of the equivalent outdoor air approach, and flushing and energy recovery. There are others there that are important. You see that UVGI is addressed, but these are the key ones that come out of the core recommendations. So system evaluation should look at both components and the systems that they are part of, including control sequences. And one of the things that goes on here is evaluation of the capacity for upgrades. How much outdoor air could we bring in if that's what we were going to do? How much can filters be upgraded in the different parts of the system, whether it's a central air handling unit or fan coil units or our VRF cassettes or whatever it might be, and what is the potential to add air cleaners either within HVAC systems or in spaces. The issue of how much more plug load can we put in for portable air cleaners is obviously something that would be considered in that context. And so for increased ventilation, I've already noted that this may not be the place to focus. The better filters may be a better solution, at least to get the first increment of improvement. There are limits to increasing ventilation during cooling operation because of sensible and latent capacity limits, and for heating, it's sensible capacity and humidification load and freeze protection concerns. What this means in practice is essentially modifying economizer controls to bring in more outdoor air when it isn't actually helpful from an energy point of view. But the figure on the right, which has been used in many presentations, shows an example of influenza risk reduction in an office building comparing MERV filter improvements, the black curve with the labels on it, and ventilation, which are the colored lines that have locations on them. And so what we see is that down to about MERV 13, there is a substantial reduction in airborne infection risk without much cost increase. And after that, we've hit the point of diminishing returns. This is for central filtration. HEPA filters make a lot of sense for in-room air cleaners, but not really for central systems in most buildings. So one of the things that's covered in a section here in epidemic conditions in place is filter upgrades and how to determine whether your system can accommodate a MERV 13 filter. And I've borrowed one of Marwa's figures here to show that there is perhaps not as much variation in pressure drop across different MERV rated filters as we tend to believe. There's not a single valued relationship between MERV rating and filter thickness and pressure drop as those data show. But there are some concerns. So the size of the racks, the leakage around the frame, which needs to be dealt with. The higher the efficiency of the filter, the more important preventing leakage is. The impact on fan capacity and the impact on energy use. One of the things that we've discovered during the pandemic is that while a MERV filter rating tells us a lot about a filter, it doesn't tell us as much as we thought. Not all MERV filters of a particular rating are going to have the same efficiency or even a very tightly clustered efficiency relative to PM 2.5, which is basically what we're concerned about. And again, here's one of Marwaz Attari's figures that illustrates this quite clearly, that you can see that there's quite a spread in PM 2.5 removal efficiency within a given MERV rating. So we may need to do some verification of how filters are working, or get information from the manufacturers that's more detailed than what we get simply with a MERV number. Another section that I pointed out was this equivalent outdoor air section. We introduced a concept in the discussion of core recommendations as to how this can be calculated. When you actually apply it, it matters not just what the efficiency of the component is, but also how it's installed and used in the system. So for a single pass filter or air cleaner, the equivalent outdoor air that it produces from the point of view of infection control is the recirculated room air flow rate multiplied by efficiency. But if we have series filters or air cleaners, then we need to use the combined efficiency, and that's not simply additive. You don't put two 50% air cleaners together and get 100% performance. So that needs to be assessed. And we can also, as far as ventilation is concerned, adjust these equivalent outdoor air quantities for ventilation effectiveness, just as we do in ASHRAE standard 62.1. If we have better, for example, stratified or worse ventilation, say if we had overhead heating, where we would be likely to get bad stratification during the heating season. So some examples here. Here's a simple recirculating system with a filter in it, and let's say the supplier is 6 air changes and the outdoor air is 2 air changes. So we've got 4 air changes recirculated, and let's say the filter efficiency is 70%. So we've got, out of these 4 air changes, at 70%, 2.8 air changes of clean air. We don't put the whole 6 through it because 2 of it is outdoor air that doesn't have contaminants in it. So this has got to be based on only the recirculated quantity. So if we take 2.8 for the filter and 2 for the outdoor air, then we have 4.8 equivalent air changes here. If this were a variable air volume system, note that as the supply air flow rate changed, this number would be going up and down. It would generally be going down because we'd be reducing the recirculation. Here's another case where now we're putting an air cleaner in series with our filter. So again, we've got 6 supply air changes and 2 outdoor air, so 4 recirculated. And we'll say we're putting an 85% single pass efficiency air cleaner in series with our 70% filter. For a series arrangement, the efficiency of 2 devices in series would be as shown here. And so that works out to 96% efficiency, combining 70% with 85%. So our 85% efficient air cleaner only added 26% to the overall performance. That gives us 3.8 air changes for filter plus air cleaner and 5.8 for the combination. So we added a 85% efficient air cleaner, and we got 1 more air change of clean air. And this brings up the point of what's better, putting an air cleaner or an enhanced filter in a central system or putting it in the space. We've just seen that because it's in series with the filter, this air cleaner doesn't do as much as it could. But if I put it in the space and it was taking in air at the space contamination level, it would do more. So If I simply move this air cleaner at the same flow rate to the space, now I get 3.4 air changes out of it, plus the 2.8 that I was getting from the filter, plus the 2 from the outdoor air. So now I've got a system that has 8.2 air changes, which is going to have a much bigger impact on the exposure levels. There is in the ASHRAE guidance a link to a calculator to help you figure this out. I'll just show it here briefly. It's a Google Sheet spreadsheet, and you can put in information on airflow rates and filter efficiencies and air cleaner efficiencies, and it will help you calculate that overall clean air supply rate. And now let's go to the flushing guidance that's in building readiness. This was talked about before. The one thing I want to say here about flushing strategy or flushing control is that from one point of view, you don't have to do anything, just get people out of the room, and if the system continues to operate, it's going to flush it. The basic idea is that there's an exponential reduction in concentration as we continue to ventilate. So we can calculate the air changes that it takes to get to a certain level of reduction. And we can also, if we have a certain air change per hour flow rate of uncontaminated air, calculate the time it takes to achieve that. And we've already discussed 95% 3 air changes, 99% 4.6 air changes. So what happens if we have, again, our 2 air change outdoor air 70% efficient filter with 4 air changes of recirculation system? We've got 4.8 air changes, so 95% reduction takes 1.6 hours. If we're only considering the 2 air changes of outdoor air, but if we take the filter into consideration, that drops to 37 minutes. So this is how using the effect of multiple controls, not just outdoor air, to determine how much flushing is necessary can make it much more convenient to turn spaces over and flush in between. I'll mention briefly that there's quite a bit of guidance on evaluating energy recovery wheels. The main thing is that the pressure relationships are such that the leakage through the seal goes from the supply side of the system to the return side of the system. And the recommendation is that the downstream supply side static pressure be at least a half an inch water gauge higher than the inlet side of the exhaust. And this should be checked in installation. Again, there are some configurations that are generally considered safe and one that isn't safe, and there's copious guidance on how to do this evaluation in the building readiness section. And then finally, the return to normal operation. These are a few things you would do after the pandemic is over and we're going back to normal. Flushing the building is before reoccupying and going back to normal is one thing that's recommended. Flushing water systems and checking water treatment. And this is if the building has been shut down to make sure that we're not exposing occupants to risk of Legionella and other waterborne pathogens. Returning the BAS to normal operating conditions, running and monitoring the systems for at least 24 hours to make sure everything that's working, and checking trends and identifying any problems, and then updating system manuals if any changes have been made. So it's really kind of a soup to nuts set of guidance for what to do going into the pandemic, during it, and coming out. And so to summarize, the core recommendations are this concise description of what ASHRAE is recommending to reduce airborne infection risk, and we think we've gotten to the point where their guidance that tells us how to do that effectively, safely, and sustainably. The building readiness guidance is an elaboration of the core recommendations that focuses on how to actually implement them, evaluation, identification, and implementation of control measures, procedures for opening buildings after shutdown, and for preparing to return to normal. And again, as always, I would encourage everyone to stay current on what's at the ASHRAE website, because it does change from time to time, and you may be using superseded guidance if you don't stay fresh with what is posted at ashrae.org/COVID-19. Run over a little bit here, and sorry about that, but I think we still have plenty of time for discussion, and appreciate your attention. Thank you.
Oh, and thank you, Bill. No, you were very well timed. It's 11:22. We have some time for some questions. I have a very basic question here. I think it got brought up at the very beginning. If you don't have the ability to spend a lot of money and upgrade your facility, especially when we're talking about schools, does simply installing ceiling fans in a room, do they help contain the virus, or do they actually help distribute the virus?
So within a space, a ceiling fan is going to distribute it. I think if you have a fairly large volume to deal with, if you have high ceilings, mixing in that volume that's outside of the breathing zone, out of the occupied zone, can be helpful. A ceiling fan by itself isn't a protective measure. If you put someone in an unventilated space with a ceiling fan, that would be exposing them to a high risk. But if you have ventilation and air cleaners and filtration that's being used, then mixing the air can actually help. And in fact, this came up just yesterday. I was in another webinar, and we were talking about healthcare and about the motivation for having such high air change rates, recirculation rates in healthcare. So in ASHRAE standard 170, you may have 6 to 12 to even 20 in some cases supply air changes for those systems. And one of the reasons that was noted by someone who develops guidance for the Veterans Administration healthcare facilities was that helps to ensure that the contaminated air in the room gets to the filters that are in the central system. Otherwise, you may have non-uniform concentrations develop, and poor air distribution will result in there being hot spots and depleted zones. So the general idea of gentle, if you will, mixing of spaces is that by reducing the concentration that anyone is exposed to, as long as you're providing other controls at appropriate levels, will tend to reduce the overall risk.
So combining, let's say, a ceiling fan with an in-room air purifier would make a lot of sense.
Right, because you're going to tend to clean the air around the air cleaner, and they generally don't have produce as much air motion as it would take to turn over the whole space. So having air cleaners working with good air distribution in the space is important. And of course, some comments were made about, well, maybe upper room UV isn't something that you want to use in a lot of spaces, and I don't disagree with that, but more air circulation in a space combined with upper room makes it a lot more effective, as has been shown in a number of studies that have been done about tuberculosis control.
Thank you. Yeah, someone actually made the expert comment that the fan would be a good way to promote the mixing in the space. And I guess you would agree with that.
Yeah, if you have it, use it. Again, I'm not advocating, I don't think ASHRAE is advocating installing ceiling fans, but they can serve a useful purpose if they're used properly. And that's something that, for example, warehouses are looking at. Is there a risk reduction strategy that would involve how they operate their fans? Should we be turning them off, or should we be operating them updraft or at lower speed? Quite a active area of investigation right now.
Right. One of the comments was doesn't MERV 13 slow the HVA machines down? And this is a question and a concern. A lot of my clients, especially community colleges and schools that have 30-year-old systems, and all they have is a 2-inch pre-filter slot that originally was MERV 8. They can upgrade to a 2-inch MERV 13, but they know they're going to have a higher static. What do you say to those facilities that only have a 2-inch space for a pre-filter?
Yeah, well, of course, the answer to these questions is always it depends. You are making an incremental increase to the flow resistance, possibly. If you have a constant speed fan, that's going to back it up on its curve, and you'll have somewhat less flow. But how many systems aren't over-designed? So you may be able to have reduced airflow and still meet loads. That's certainly been the case with residential systems, and residential systems may actually run better if the airflow is somewhat reduced, because they may not cycle on and off as frequently and give better humidity control. There's been a problem with systems that cycle where they dehumidify, they hit set point on the thermostat, they stop, and the moisture on the coil evaporates back into the air, and then you just keep evaporating it and condensing it. If you have a VAV system, of course, as long as the fan has enough capacity, then the system is going to provide however much air it takes to satisfy the needs of the spaces. So in that case, there may not be any reduction in flow rate, but there may be an increase in energy use. There's not a single answer to that question.
Right. Yeah. I would assume that there's no single answer to any question when it comes to a new situation, an extraordinary event like we faced here in the pandemic. I'm going to show my screen for just a minute, and I want you to comment on what you think of this. Hold on a second. Show screen. And
I'm seeing some MERV 14 filters in a box.
yes. So here is exactly what I was talking about. This section was actually put on to this 40-year-old package unit. I believe it's a train package unit with 2-inch filters. And I consulted the client to do a balancing study, an air balancing study. And they actually found that they were a little below ventilation standards. And therefore, they were very concerned about any kind of upgrade to a MERV 13 2-inch. So we weren't able to do this in all the systems because some of them have plenums and other obstructions. But what we did for this client was we strapped in some front access frames, and we then installed MERV 14 V-cell high capacity, high performance filters. What we actually did was we reduced the initial static while increasing MERV 8 to MERV 14. They're spending a little more on these filters, but these filters, we are expecting them to last 18 months. So instead of changing the pre-filters every quarter or sooner, they're going to be changing filters once every year and a half. This section has been in operation for about 7 months, and the static pressures have barely moved. The filters are a little dirtier now, but what do you think? What do you think of something like that?
Well, it seems like a good option where applicable. You know, obviously, increasing face area on filter systems is one way to overcome the problem of increased pressure drop, and I've seen that used in a number of cases. So I think it looks like a good solution for the places you've applied it.
Can we get back to the humidity a little bit? I've just read so much information about operating at 40 to 60% relative humidity control. It seems that I've been reading that it does drastically reduce the ability for any virus to be transmitted through the airstream, and perhaps through the ductwork, through a filter, through a cooling coil, through a supply fan, back down through the supply ductwork, and back through that supply grill and into that space, which is what we're really concerned with. You mentioned the cost, and it is a huge cost in many facilities. In some facilities, it's not possible because of the envelope and the way that the building is configured. But where it's feasible, it seems that the reports that I've been reading show that the increase to the overall indoor air quality is just dramatic. And I'm wondering why it wasn't pushed up a little further into the core recommendations with the caveat of when you can do it.
Well, because we're looking at engineering controls, and in the scheme of things where we're trying to assess what is the overall removal rate or inactivation of infectious aerosols, how does it compare to other things? Lindsay Marr has done a lot of work on this that I mentioned, and if you read her papers, what they say is that there are some viruses that inactivate more rapidly as humidity increases. There are some that inactivate less rapidly as humidity increases, and some that are not very much affected. So that's one thing. Right now we're talking about an envelope coronavirus and how it's affected by humidity. The second thing is, as shown in her work, even though there may be an effect, you have to consider that in the context of the other controls. And maybe it's not such a big factor when it's combined with them. I mean, think of the example that I gave in my talk of what happens if you put an 85% efficient air cleaner in series with a 70% efficient filter. You get another 26% out of it. So it looks much better than it is when you combine it with other things. And I think that's the thing that makes us reluctant to say that this is something that should be at the top of the list. And I always point out when I say that I think that there were plenty of other good reasons to humidify. But would I upgrade filters or put in an air cleaner, or would I buy a humidifier? If I was rationing the funds that I had to spend, where would I spend it? And I don't think I would. The humidifier would be the first thing I would go out and buy to make myself safer. I'm not saying it doesn't have an impact, but when you look at some of these risk calculators and look at what's the difference, say, between going from 20% relative humidity to 40% relative humidity in an office building in Chicago, that looks like maybe an air change per hour in additional inactivation compared to the energy cost of doing the additional humidification. So we're not discouraging it. We're just saying we're not encouraging it strongly because we think there are other things you should do first.
Absolutely, absolutely agree. So we're at the end of our second presentation. Bill, the Society is so thankful for not only you being here this year, but you being here for the first annual event in 2020. We're proud that it was your first teleconference last year. Now we call it a webinar. So thank you so much. If you can stick around for the panel discussion, that'd be great, but we understand if you have to go. If we get any questions, anyone in the audience, if you have specific questions that you think of, please send them to me. I can relay them to Bill, and I'm sure he will take the time to answer them. We can get you the answers that you need. So we're going to go on a 10-minute break right now. We're going to come back at exactly 10:45 to listen to Jeffrey Rios from AKF Engineers talk about electrification of buildings. the discussion of carbon versus energy. But once again, Bill, thank you very much. And to the audience, we will expect everyone back at 11:45. Thank you very much.
And pretty solid in terms of the minimizing carbon. Our sort of mid-range option, where you have the air-to-water heat pump feeding the water loop heat pumps in the building, is not great. It's kind of, today, it's not the best solution. It's a little bit inefficient because we're running compressors twice. It's a little bit of a challenge to get that operating perfectly. So it's not the best solution. You see there, related to that is the energy cost. The really efficient option of the air source heat pump with fan coils is the lowest energy cost, but it's not a giant savings against sort of a baseline system. Gas is still cheap relatively to buy from a utility standpoint, so that does put the all-electric solutions at a little bit of a disadvantage in terms of the cost savings, but they are all reasonably efficient systems in terms of operating costs. We will see potential of some annual cost savings from the VRF and the air source heat pumps. That's something to note. And as we start to see local I-97 fines creep into buildings, there will be a savings potential on fines relative to the gas-fired system. The one item here, the second to last item here, is just a potential capability to provide domestic hot water. Any of the loops, any of the systems that have a water loop in the building, which is the condenser water loops with options, the base option and option 2, and the chilled water hot water loop and option 3, those all potentially can feed a water source heat pump to provide domestic water. That's something we're looking at designing in a couple buildings now. It's a pretty good solution, and it is a much easier way of addressing domestic hot water within a residential building than is a VRF system. So that's something to note. And then finally, just to kind of circle back on this, the incentive potential. Con Ed has come out with a pretty new program in the last few months. It's called the Clean Heat program. It's really sort of targeting and trying to incentivize clean heat from heat pump technology. There's real money out there. I mean, we have started the process in a couple of projects currently, so I don't have a great sense of it. It's a relatively new program, but for very just for discussion, we're seeing the incentive potential. You know, it might approach half of the first cost increase of some of these all-electric systems or more. So it's significant. It might be enough to change the math and change the argument for these systems. So that's something to note. Then just in conclusion, to talk about this a little bit, this is sort of like energy versus cost. You know, you see the worst carbon is our baseline tower boiler system, but our worst cost is sort of our air-to-water heat pump feeding our water loop heat pumps. Again, that's a little bit because of the efficiency of that system versus the VRF and air source heat pump and fan coils, but also because of the cost of gas. So it's something to think about. Gas is still cheap. It is something you have to consider when you're looking at these systems. You really want to look at an all-electric system that is very efficient, because otherwise you're going to be looking at the potential for some increase in annual operational costs as electricity rates are today, right? So in conclusion, we don't quite have the Tesla for buildings, but we're getting there. And again, it's a little bit more of a challenge on buildings than it is for cars, just by virtue of where we're starting from, right? The efficiency of a car engine versus a building gas fire system. So that's all I got. I'm happy to open it up for questions.
Thank you very much, Jeffrey. Very much appreciate your time putting together that presentation. Is it really feasible to electrify a high-rise building in New York City?
That's a great question, Scott. I think, you know, I think this is something that a lot of us are struggling with. I'm sure we will have a conversation on this in the, when we get into the panel, because this is a question that's on a lot of people's minds today. So I will say, yes, it is. I think there are challenges with it, right? So the two examples that I kind of was talking about were residential buildings. They are high-rise, you know, do meet the high-rise definition. They're both, you know, 15 to 17 stories tall, but that's not, you know, 2 million square foot high-rise, right? So obviously, it's more challenging the taller and you know, height to footprint, less outdoor space relative to footprint it becomes more challenging. But there are solutions to get us there, and I think it's just, part of that equation is just really changing the conversation with how much space we need, where we might need mechanical floors with a lot of louver area and that kind of thing. So it's certainly possible, but there are still challenges with it today. I think that's the takeaway.
Yeah, I was referring to large commercial buildings, where residential complexes are usually very standard, same system, floor by floor by floor. I assume for a high-rise building, you kind of look at it as piecemeal, 4 floors here, 5 floors there, one tenant at a time. Would that be the way to deal with a commercial building?
So we've spoken to a number of clients on this. That is one way to approach it. And if you're looking at, sort of like a VRF type solution, I think that's the right approach, right? You need to have limitations on how far you're running stuff, and selecting it by tenants and giving each tenant their own VRFs, their VRF farm, and letting them run with it is a solution that works. We are also looking at a number of sort of more centralized systems with sort of this water distribution. So like the air to water heat pump system is something that can work in a commercial building. It's just going to require larger floor areas and larger outdoor connection than would a traditional tower boiler system. But once you're able to make the cooling and heating water, you can distribute it in a very similar fashion to what you might have done with a conventional system.
Maybe I missed it, but are there any government incentives, NYSERDA incentives, to implement this type of electrification of buildings?
Yeah, well, so that's what I mentioned at the very tail end there, Scott. I mean, there are a number of different programs. I think most recently, and probably the most significant one, is the kind of clean heat program. It's come out within the last few months, and there's significant money available, and the program really is focused purely on heat pump technologies and moving towards efficient electrification of heating, both for domestic and space heat. So that's, I think, there's probably other ones that would apply potentially as well. That program specifically in New York City is a very, there's some real positives to it.
And so are we talking about getting rid of cooling towers?
I mean, yeah, that's a good question. Getting rid of cooling towers, I think, has a lot of positives otherwise, right? There's been all the Legionella concerns over the last several years as well. I mean, I think, there's a lot of benefit to having a system that does both heating and cooling, right? And if we're going with a water source system, the air to water heat pump can do both cooling and heating. And more often than not, in our Northeast environment, the systems would be sized for heating more so than cooling, which means you don't need cooling towers, right? If you have an air to water heat pump that can do cooling and heating for your building, there's no need for a cooling tower. So, does that mean that cooling towers are going to go away forever? Maybe not. I mean, cooling towers from a cooling standpoint are still pretty efficient systems, right? But they don't do heating, and I think that's most of the solutions we're talking about now would be both heating and cooling when you start talking about electrification. So, if that's the way things go, then it would likely, yes, certainly minimize the number of towers.
Can you just speak for a moment? During Bill's presentation, they made a recommendation at the end in his summary that as facilities start to reoccupy spaces, and I've read about this in a number of articles, can you talk about what you're recommending to your customers, how to deal with the stagnation of the water systems, of the condenser systems and such?
I'm sorry, I'm not. You're talking about for buildings that have been unoccupied completely, where the towers are off.
Right. So I'm getting a little away from the subject matter, but I just thought it wasn't discussed from Bill's presentation, and I just thought it's extremely important for buildings to understand that that is one of their priorities that they need to have of how to deal with that. Is that a commissioning task that, like an AKF would do?
Yeah, I mean, I think that, we've had a number of buildings that have talking about reoccupying, and yes, commission groups across the city, I think, are looking at that problem, as well as, just on the air side as well, making sure all the equipment's working if it's been off for any period of time. I think treatment, definitely bringing in your treatment vendors and making sure that that stuff is properly operating, in addition to commissioning agents, is an important factor for making sure all of those systems are up and running, ready to go, and not, you're not going to see sort of, obviously, if you start running a cooling tower and it's been stagnant for a long time, there's other significant indoor or air quality concerns as well, potentially.
Yes, significant. I mean, just so significant. The liability is tremendous when you're dealing with a cooling tower. And I've seen a lot of buildings now spending a large part of their budget just testing towers continually. And so I would think that would be kind of part of the push to electrify a building.
Just getting away from towers, essentially.
Is getting away from towers, essentially.
Yeah, for sure. I mean, I think, like taking an example of that case study I just presented, just kind of talk through it. Certainly one of the positives of some of the all electric solutions is we don't have a cooling tower, right? There's neighbors around that building. There's windows within a certain distance of that tower, all code compliant, but, always potential concerns, risks, even if nothing else, just complaints from neighbors, right? So certainly a positive for sure of those all electric systems.
Are you finding this rooftop equipment to have any acoustical issues? I assume it's
they're louder. Most of these are louder than a cooling tower would be, right? They're though they're all big fans, right? They're all kind of fans operating as a with compressor. But yes, not things we can't mitigate, but it definitely has to be something looked at with an acoustic consultant, depending on how close you are to neighbors.
Absolutely. So one of the concerns I've always heard about in going to VRF systems and being not only a voting member, but vice chair of ASHRAE's TC 2.5 Global Climate Change Technical Committee, is there's obviously a major push to go with refrigerants that are not ozone depletion, and now the push is to go to low or no global warming potential refrigerants. But one of the concerns within the community is that some of these refrigerants have a higher flammability index. And now we are putting these small VRF ceiling mounted units everywhere, above every head, every desk, and the refrigerant piping inside the building, even though it's a very small diameter tube, it's pretty extensive. Have you heard of any concerns or any discussions regarding
Absolutely. That? Yeah, absolutely. I mean, whether it's the more flammable, lower global warming potential refrigerants, or just conventional refrigerants that have been around for a long time, I think there's a concern in either case. Certainly, one of the negatives of a VRF solution is that it does have refrigerant piping running all over the building, right? There's concerns from, both whether it's flammability or just, again, indoor air quality. Any leaks in that scenario is obviously very potentially harmful. Those are negatives of that system for sure. Just like the cooling tower is a negative of that cooling tower system. So that's, I mean, there's lots of conversations that can be had around that. And I think every building is different in terms of the length of run and potential concerns with, making sure we're monitoring and having leak detection on all those systems. But that is absolutely a concern.
Is that something that you've been going through with your clients as they've come to you to discuss preparing and being ready for the reopenings and or the occupying of the spaces due to COVID-19?
You mean not specifically that refrigerant discussion? I think that's a little bit, I think that's potentially a concern all the time. I don't know that there's any significant increased risk relative to, having been dormant during COVID. with a VRF kind of solution. And that's not something I don't think we've been having significant conversations on. But it's always a conversation with that type of system. And I think, the sort of reoccupancy, there's a lot of, the cooling tower one is a very real concern with reoccupying a building.
Nice. What do you see as your client's major concern when you discuss the electrification of buildings?
Probably costs. I mean, not surprisingly, right? Costs are always a concern. Most of the all-electric solutions still cost more today upfront. I think that is that's real. I think some of the incentives might change that dynamic a little bit. That's helpful. But then the other component of this is there's first cost and there's operational cost. Gas is still really cheap. So it's not as much of the savings that we'd like to see. And in a perfect, very efficient system, we can have the utility cost savings. But relative to purely gas-fired boilers, not all of these solutions are going to see any real utility savings annually with the rates as they exist today. So that's, it's a hard argument to say this isn't going to cost you more and it's going to cost you more to run it every year. It's a challenge. So that's definitely a concern. I think things are changing as things get more and more efficient. Utility costs annually will go down as incentives come out and sort of start to push that electric solution. That'll change the first cost dynamic as well.
Do you foresee cogeneration being a greater part of design, generating on-site?
So that's a really good question. In fact, in a lot of ways, the push towards electrification really flips the need for cogeneration and kind of makes it not effective because most cogeneration systems are utilizing fossil fuel to produce energy, right? I think, there's been a lot of discussion on that. We have a lot of clients asking about that. Folks that have cogeneration systems currently and folks that have been considering putting them in. I think, there's a lot of, so I talked a little bit about the grid and what the grid looks like today and what it might look like in the future. I was talking in a very, very simple way around just assuming it's the same all the time. And that's not the case, right? Electricity is produced different hours of the day, and depending on when it's produced, that energy comes at a different carbon cost. So where cogeneration and any sort of on-site generation might have viability from a carbon standpoint is kind of like working with utility to offload the really inefficient carbon emitters when it's generating, right? So that's something that I didn't get into, but there is a lot of conversation around that within the local Law 97 working groups as well. Time of day, time of use, consumption. That's a concern. That's a topic of discussion. And that's where lots of things, cogeneration, thermal storage, any sort of battery storage, all of those technologies start to play a role when you look at time of use, carbon, in addition to time of use cost.
So you see the use of thermal storage and battery storage as a cohesive strategy with electrification?
Yeah, it certainly can be. I mean, I think to be quite honest, I think it's a little early to really understand how to do that. And what I mean by that is there's not a great consensus around how to treat the time of use, both from we have utility programs that have had demand charges and pricing for that kind of technology for a long time. So that's known. We've done in the past, and we can anytime go in and design an efficient thermal storage system or cogeneration system to respond to those prices, right? What's not well established yet is what time of use carbon looks like, right? What does that look like if you use, more electricity at 3 o'clock in July on a weekday versus what you use in the wintertime, right? That's not something that's well established yet. And I think until that is established, it is difficult and it's challenging to really fine tune that interaction of thermal storage, battery storage systems within an all electric building or within any building.
Are your clients still focused on local law 97 right now and over the past year?
I would say I wouldn't say focused on. Obviously, everybody's been focused on a lot of things this last year, right? I think that's a fair.
Let's hope.
Right. But yeah, no, people are still talking about local 97. It's still a concern for owners. I mean, I think to some degree we've seen a number of folks You know, a lot of our clients, as I'm sure a lot of folks' clients have kind of taken a step back this last year, right? Especially commercial office buildings, to kind of rethink things. And some of that step back and rethink has been focused on Local 97, right? Maybe it's a little bit of, you know, they have some time starting to look at some evaluations of their buildings and what it might mean relative to Local 97. So I think it's certainly, I think, you know, the last 12, 14 months have changed the way people would have been talking about Local 97. But it hasn't gone away. I mean, I think it's still a topic, and it's still, you know, potentially some of these mitigation strategies we are trying to figure out, you know, similar to what Molly and Jonathan talked about earlier, and some of what Bill went over. We're trying to think about efficient ways to provide better indoor air quality and mitigate COVID. But a lot of them, even if we do them efficiently, are going to have an energy impact. So all of it goes together, and I think that all kind of ties to Local 97 as well.
So, you know, when I survey buildings for upgrading their air quality, we always, of course, look for the low-hanging fruit, just like in the lighting industry. If you have an incandescent bulb, that's a no-brainer. But if you have fluorescent bulbs, the move to LED is still smart, but it's not the same energy savings that you'd see from going from incandescent. And when we do UV surveys and we see a coil that looks like, you know, a forest, it's very simple to realize the effectiveness and the savings that we can show the client. When I first came into this industry a long time ago, everyone was on steam turbines, high pressure steam turbines. There wasn't a building I walked into that didn't have a 30, 40-year-old York or Carrier single stage absorber. And then we saw the train absorbers, and then the two-stage absorbers, the chiller heater absorbers. It seemed always to me that it was a steam-centric city. What would you consider the low-hanging fruit building, the best opportunities that are the easiest targets for electrification?
Yeah, a lot of that, Scott, has to do with the distribution in the building, right? So if the building has existing steam pipe distribution, that's a more costly impact to renovate that with an all-electric solution. There's no good way of making steam with electricity right now. Back to the, you know, it's got to be an electric resistance boiler. It's going to be really inefficient, and from a carbon standpoint, it's going to be a detriment. So lower temperature hot water is the way to do electric, right? In terms of conversion. So buildings that already have water loops and hot water systems that are not super hot water temperatures. That's probably the first place to go. Then you have to start looking at envelope upgrades to really mitigate the thermal loss and what you can do with lower temperature waters versus what the old distribution system had done in coils, right? Can you replace coils to get more out of lower temperature water? But I think the first thing to look at is distribution. What's your distribution system? And if it is steam, then you probably want to start planning for a longer term solution. Like, it's going to be costly today. What do you want to do? You know, how do you want to set yourself up for 10 years from now to get off that steam system? Because you might be fine for 10 years, but it's probably not going to be something you want to do forever.
Right. What I've seen, I've walked into so many buildings that are completely empty for the last 12, 13 months. And some of them are just going through massive renovations floor by floor. I would assume that's the best time. I mean, that's really the best time to, when you're ripping out a floor, to get rid of your steam system. Okay, so we're going to cut away. Thank you, Jeffrey, very much. Jeffrey will be back for the panel forum. We're going to take a 10-minute break, and we're going to return at 12:45, where I will introduce the partners of 5 large MEP engineering firms. They're going to give a very short presentation, and we're going to open it up for more questions. A couple of questions just came in, and we will hold them off for Jeffrey and the other electrification experts that we have on the panel. So thank you once again, Jeffrey, and we'll see you in the panel. And audience, please return at 12:45. Thank you.
Thanks, Scott.
the post-lunch coma. So hopefully I can bring you out of that. We'll see. And I'm going to kind of take it a different way for, I have like 5 minutes here. I'm going to kind of take it a different way, talk about something maybe a little more on the macro scale. Right, so Jeff mentioned in his previous presentation about the state's requirement to green the grid, right? We're talking a 70% renewable grid by 2030, 100% renewable by 2040. And with that, grid level energy storage is going to be a critical component, right? In order to sort of level out the peaks and valleys of the peak electrical demand of buildings and their impact on the grid. And so, I have connections up kind of in the upstate region. And there was a proposal submitted by a company called Premium Energy Holdings. It's a California-based company, and they submitted a proposal for a pumped hydro grid-level energy storage project in upstate. The proposal was submitted to the New York City DEC and DEP, and here's like a little map of, this is from their submission. On the left-hand side, you see the New York State, and the little red dot is where the project is located. It's just, this is about 100 miles north of New York City, kind of in the sort of Catskill Park area near Woodstock, New York, if you're familiar with that area. And the map on the right is in light blue is the Ashokan Reservoir. If you're not familiar with the Ashokan Reservoir, it's one of 5 reservoirs that were built by New York City back in the early 1900s in this area. It's the largest one of the reservoir system, and it's actually the deepest and holds the most amount of water, and serves 40% of New York City's drinking water. So, but you can't just build a reservoir, without impacting someone. There was originally a valley there. The valley had communities and towns and people, making their way of life there. And when the reservoir came in, by eminent domain, the city vacated these entire communities and relocated them to make way to flood this 15-mile long body of water. So the reservoir exists today. It's serving drinking water from New York City, and this whole area is very, very sort of pristine. It's very natural. The kind of the big green blob on the left there of that map is part of the Catskill Park. To put that in perspective, that little green swath right there is about 60,000 acres of forever wild state land. So this is a very natural area. Well, the proposal came through from Premium Energy Holdings, and the proposal consisted of building a 230-acre elevated reservoir shown on the left side of that map, in sort of an elevated valley, where the water level of the elevated reservoir is going to be about 900 feet higher than the elevation of the main reservoir. But the idea being that, when energy is plentiful, the solar energy going to come on the grid in the next 10 years. When that energy is plentiful, the idea is to pump water from the main reservoir up to the elevated reservoir, so that when energy is not plentiful, right, when the sun is not shining, water can drain by gravity through a buried tunnel, through a turbine, and produce electricity to sort of level out those peaks and valleys of the grid. It's a pretty classic method of grid level energy storage. It's tried and true. It works very well. And it's also considered what's called a long-term energy storage solution, right? Where lithium ion batteries are good for a certain number of hours, right? They're idealized from a cost perspective for a certain number of hours. Pumped hydro is something that can last days, weeks, right? The water can sit at stasis in the elevated pond and be very effective. As part of this proposal, there's a 300-foot long dam to hold that elevated reservoir, 230 kV overhead transmission lines, a 40-foot diameter, 1 mile long tunnel to carry the fluid water from the elevated reservoir to the lower one. All the while this being built on state land, partially on state land, partially on private land, but very, very impactful, this project. And as you can imagine, the community, and if you guys know anything about Woodstock, very natural sort of community there was a really strong opposition to this plan, very strong. And immediately there were Facebook groups formed and websites and community leaders coalescing around fighting this plan. There were talks at the local library, by lawyers and by folks explaining why the proposal was flawed and why it shouldn't happen and why we should protect it. And there was very little link between the benefits of the proposal, the technical merits in terms of the actual grid level storage and sort of the decarbonization aspects. It was just kind of like bad. And ultimately the proposal did fail. It was retracted just kind of in about a month ago, 3 weeks ago. And it didn't fail because it wasn't a good technical proposal. In fact, I think it was very good. I mean, if you read the whole thing, it was very technical, provided all the right numbers in terms of electricity production and the impact, et cetera, et cetera. I mean, it failed, I think, because it was thrust into a community that really wasn't really ready for it, didn't understand it. And a community that had this deep-seated resistance to infrastructure for others, right? As I mentioned, the reservoir, when it was built, displaced these whole communities. And so there's an undercurrent of sort of, anger associated with this giant infrastructure project of building the reservoir and how it wasn't directly impacting the residents in the area, it was impacting and helping people elsewhere, meaning in New York City. And in this case, we're talking about new technologies, we're talking about a change to the landscape, the natural environment, the loss of land, a big dam to hold back that reservoir, which is unsightly. And, like I mentioned, the people that are really directly involved here, the locals wouldn't see the benefit. They wouldn't really see it and feel it, much like the construction of the reservoir itself. And so, I only have a couple minutes here. It's like a little intro. When I think about what we're doing in New York City and all the stuff, even that, what Jeff just mentioned and all these new technologies, I really do see a parallel. Electrification is also very new to so many people. It's really hard, it's challenging, it's impactful, and it affects the business as usual way that we serve our buildings right now. And it's a big change, and when we make proposals for new technologies, like the air source heat pumps, we're talking about new massing to accommodate those air source heat pumps, new ways of purchasing energy, renewable energy, sometimes cost increases associated with electrification because of the 5x cost of the fuel versus gas. We're going to see resistance, and we're seeing resistance kind of across the board. And all this is like really new, and I think is natural for people to be resistant to the change, especially, and in the context of today's seminar, especially after this crazy year with all of this change that has been pushed down to everybody kind of from somewhere else. And so, I think this is actually a really big hurdle, and I don't think it's a hurdle that we talk about enough. We're so focused on what's the right technical solution. Sometimes we miss the way we're conveying them. And so I think that, if the solutions that we're developing aren't properly, conveyed, I think if we don't spend enough time on the engagement with the team, especially the building operations team who are going to get so impacted by this, then regardless of how good our solution is, it could potentially fail, kind of like the reservoir proposal failed. So, you're saying, oh, well, how do we make sure this doesn't happen? And I really think it's about engagement. The proposal failed upstate in part, the proposal upstate failed, in part because it was something new. It was thrust on the community. There was no transparency about the why. There was no community engagement. And so I think to succeed at our projects, these electrification projects that are so challenging, I do think we need the right technical solution. We have all these amazing engineers on this panel that are working on these great solutions. But we also need to engage differently with the owners and the tenants, and most importantly, the building operators, in a way that we haven't before. And I don't mean just like our normal kickoff meeting and our normal presentation, our normal like follow-up, and this is what you should do. I think it's got to be way more than that. I just don't think that's good enough. We have to be part of the process to help remove all the uncertainties and to make it easy. We need education, on energy, and every conversation should start with policy as to why we're doing this to begin with. Training, I'm thinking about, groups like BOMA, and REBNY, and even more from ASHRAE. I think this is sort of like an open call that I think we need more of this sort of, more of this focus on the process, to get everybody on the same page. And, because honestly, I do believe that if we don't put our arms around the whole thing, this whole start to finish, then I think we could fail at succeeding. And obviously that's not where we want to be. That's not an option.
Thank you, Chris. I'm going to turn the screen over to Amy MacDonald now from Thornton Tomasetti. Very nice. We see that up on the screen. Welcome, Amy. We don't have audio yet. Let's see if we can correct that.
I think I'm unmuted now. Does that work?
Yes. Yeah, there you are. Very
Okay,
good.
great. Okay. And you can see my full screen?
You're still in the your PowerPoint. If you could.
Yeah, but can you see the presenter mode or the screen share?
It's the screenshot. If you could slideshow it.
Okay. Yeah, it is slideshow. I just have two screens. Is that better?
Yes, it is.
Okay, cool.
Excellent.
Great. And now that's to work. How do we go next page? Okay, right. It's working now?
Yes, it is.
Okay, excellent. Right. Well, thanks so much. We're going to switch gears a little bit and talk about the concept of resilience. We've talked a lot about sustainability today, and kind of touched on aspects of resilience for sure. But so I'm the principal and head of resilience at Thornton Tomasetti. I would argue that we're not strictly a MEP firm, but we do have some MEP engineers. They really focus on the performance and investigation side, whereas teams like that I work on, we also work with design, so more on the structural engineering and risk side of things. So today we're just going to talk a little bit about resilience and what it is, how is it different to sustainability, and how does that context work with in the building context. So sustainability aims to slow the impact of energy and resource consumption and put the world back into balance. So with regards to climate change, I think and buildings, this is pretty obvious what we're talking about. Sometimes people get confused about what's the difference between sustainability and resilience. So the way that we've been talking about resilience is that resilience goes beyond just climate change, but we're looking for ways to manage and to thrive in an imbalanced world. And I think no better than today do we understand exactly what an imbalanced world is. So what sort of things are we dealing with? We're dealing with COVID, so let's say pandemics. We also have earthquakes, floods, tornadoes, fires, hurricanes. We have the impact of climate change, which is ongoing and increasing. So increasing both the intensity, the duration, and the frequency of these climatic extremes. The reason this is a problem is it's causing massive disruption and also massive losses. So in 2020 alone, there was nearly $175 billion worth of losses that occurred in relation to natural catastrophes, but only 43% of these were actually insured. So it's a lot that goes uninsured, which obviously is a problem for our communities. So we also continue to build and have a growing population that are exposed and located in vulnerable areas. We also have things like the continued evolution of terrorism, cyber attacks, pandemics that we're seeing right now. So this is why resilience is important. It's important that we think about these things when we're designing buildings and infrastructure, and that we plan ahead so that we minimize the impacts that they have on people, on the environment, on our buildings, infrastructure, the operations of our businesses, and obviously there's a revenue piece there too. So just a few examples of things that we've been dealing with even just in the last few months. We've had COVID, we've had some pretty major hurricanes. New York obviously haven't been impacted by major hurricane for a few years now, but that is a risk every year, sometime between June and November. We've also seen an increase in wildfires, and the reason these are problems that they have such a big impact on our communities. So as engineers, we have the opportunity to think about these sorts of things before we design buildings or as we're retrofitting buildings to reduce the impact on our communities. And it's not just the initial impact of these events either. Often we have cascading impacts. So on extremely hot days recently, we've had heat waves that have resulted in the loss of power. We have the cascading impacts of having a pandemic and the impacts of people not being able to be in their homes and needing to go into cooling centers during these power outages. On the right there, you've got some images of while Maria impacted Puerto Rico, specifically, I suppose, as a storm surge and high wind event, the cascading impacts of the power outages caused extreme hardship on the people of Puerto Rico and really hampered the recovery efforts for a long time. So one important message I'd like everyone to take away, and think that our media really do us a bit of a disservice by using the term natural disasters. So disasters are actually not natural. By calling it a natural disaster, it sounds like there's something inevitable about it, but really the natural hazards may be inevitable, but whether or not they become a disaster is not. So it's the way that the choices that we make, where we build, how we build, and what sort of infrastructure we put in, and the ways that that is constructed, and the preparation we make, that really is what turns a natural hazard into a disaster. So it's that hazard, having the exposure, and then that vulnerability, which is something that we actually all have an opportunity to reduce that vulnerability as part of our everyday work. So resilience is to prepare, to endure, to adapt and thrive in a disruptive and changing world. And we want to consider all types of natural and human-induced hazards and shocks and stresses, which we typically call it in the resilience world these days. And the best time to incorporate that approach, a resilience approach, is very early in the project. So we often find that we get brought in like during design as opposed to in the planning phase. And at that point, it becomes more costly, and our ability to make changes has reduced. So the more often we can get brought in at the master planning or feasibility stage, the greater chance we have to make the most impact on enhancing the resilience of a project for the least cost. And that applies to all disciplines. So taking a resilience approach, we need to start with the diagnose phase. And I would highlight here that we used to look at this as a linear process, but now we really think of it as a circular process, because resilience it's a journey, really. It's never something you reach a point where you say I'm resilient, because the world is constantly changing. We need to be constantly reassessing as well. So that diagnose phase is the assessment of the site-specific vulnerabilities to shocks and stresses. So that could be anything from floods and hurricanes to terrorism, to pandemics, to the impact that climate change will have on natural hazards, and understanding what those vulnerabilities are before you can actually identify and develop a holistic and integrated resilience strategy. And that really needs to consider all the different disciplines, so taking a very integrated approach. That then leads to that normal kind of stage that we get involved with is in the AEC industry, is the design and build of physical risk reduction measures that would be incorporated, or criteria that would be incorporated into the design. And then the other aspect that I think is also really important is actually the operational risk reduction measures. So part of that is that emergency preparedness piece. Your plan is also only as good as it is as the people who know how to implement it. So making sure that you're constantly reviewing and learning and innovating is a really important aspect too. So here's just a very high level of some of the different types of natural and human-induced shocks and stresses. You'll see pretty wide range up there, but you need to assess the specific site to understand which ones are relevant and which part of the country and where exactly you're located. Specifically in New York, I think that we deal with a wide range, but probably lesser of the lower part of this table. So that identification of the shocks and stresses that are relevant then leads us to wanting to, first we want to learn from what's happened in the past. We want to look to current codes and standards and any resilience guidelines that exist and current hazard levels, but we also want to consider future projections. So with regard to climate, we really want to make sure that we're considering what is going to be how is the extreme heat going to change over the years. If we're looking at plumbing, we also want to consider precipitation. The current precipitation levels are not really representative of what are projected to occur in the future, and the same goes with sea level rise. So once we understand the likelihood and the potential impacts of each of those shocks and stresses on our systems, and also understand the context, so that potential area-wide impacts. So if your entire site is surrounding your site is going to be flooded, then that might affect what sort of like continued operations are actually relevant, right? So let's say if a commercial office building is going to be, the building might be absolutely fine and elevated above the floodplain, both current and future, but if the surrounding area is going to be flooded, then we would really just be wanting to design that building for immediate resumption of operations as soon as those floodwaters around the property have gone down, as opposed to continued operations that we would be looking for if it was a hospital, for example. And then this leads us to, once we've developed this picture and the story of what the resilience gaps and opportunities are, then we can identify those solutions and how they are integrated through a multidisciplinary approach to design. So just in summary here, this was just a very quick high overview before we start our discussion, but the keys to designing for resilience are making sure that we're designing our infrastructure and buildings to survive, adapt, and thrive in the face of uncertainty. So that requires an integrated and multidisciplinary approach, early integration, taking a risk-informed and future-focused approach to design. So that's really incorporating hindsight, insight, and foresight. Thank you.
Thank you very much, Amy. I'm going to now turn over to Desmond Greene from WB Engineers. And Desmond, do you have power? There it is. Fantastic. And let me get you. Your microphone.
You
Yes,
hear
we
me now?
do.
And you can see my presentation?
Yes, we can.
Excellent. Okay. So thank you, Scott. My name is Desmond Greene. I'm Managing Principal with WB Engineers and Consultants in New York City. Thanks for inviting me to take part of this panel for Earth Day. I really appreciate it. And I'll try and keep it brief. I know everybody's been through, listening to the webinars the past three or 4 hours, and some of the topics or subjects that I cover in my brief presentation may have already been spoken to. So if it is, I apologize in advance. So my presentation includes summary of some case studies that we've done over the past year based on work that we've done with clients in the past year, and kind of ties in indoor air quality, local law 97, healthy buildings, and the impact to overall occupant comfort and productivity. So like all of the consultants that spoke today, a year ago we were working with all our clients to best advise them on how they should approach or deal with potential exposure of their staff and building occupants to COVID-19. At that stage, the primary concern was to reduce the risk of transmission of the virus, and any impact to energy usage was secondary. While this is acceptable a year ago, we're finding a lot of the buildings are coming back to us now and asking us, how is that impacting them? I know it was already discussed at the presentation this morning. And they're rightly concerned about local law 97 and the impact to any of their fines. So they're asking engineering companies to to find out what they can do to reduce that impact. Bill has already spoken today about ASHRAE's recommendations for mitigation that they developed over the past year, and those included increased ventilation, minimum MERV 13 filters, maintenance of temperature and humidity set points, and installation, or at least consideration of installation, of active mitigation systems. And that's all outlined in the excellent portal on ASHRAE's website. So in the past year, we've worked with a number of clients like yourselves in terms of introducing and developing mitigation standards for them. One of our large national clients, we were engaged to develop COVID-19 mitigation standards throughout their facilities in about 45-50 buildings. This included design and installation of UVGI systems, increasing filter ratings to minimum of MERV 13 if the units could accommodate that, higher if they could as well, and then modifying and adjusting their sequence of operations to accommodate for increased ventilation, dilution cycles, flushing of the building before and after occupancy. That program was recently completed in the past month or two. We installed a lot of UVGI systems, and now in the next 6 months to a year, we'll be assessing the impact to energy usage and the carbon emissions in the buildings. We've done some assessments and estimations, but it's difficult because these are occupied buildings. As a large corporation, even the corporation isn't quite sure how these are going to be occupied in the future. So it'll be interesting metric when we develop that in the next 6 months to a year. The other thing many of our clients were concerned about was indoor air quality, how they read it, how they monitor it. And I know that, again, this was a subject that was discussed in detail this morning. We're looking at real-time monitoring systems for indoor air quality that can measure temperature, humidity, CO2 levels, VOCs, PM 2.5s. And we can place that information on dashboards for the clients to use, to read. We can alarm them. Tenants are getting more educated in indoor air quality, and we find this like a useful tool for them to alert building owners or landlords if some of the metrics are a little high. It can also be used for operating engineers and facility managers to adjust set points, maybe repair some equipment, take a look at sensors, and also it can be integrated as part of the BMS to do those readjustments automatically. So this led on to healthy building design. There was a big push from our clients to really research and look at healthy building design in and above code requirements, including well and fit well. And it encompassed, we found a lot of the initiatives that were developed during COVID-19 by ASHRAE and other organizations. So having a healthy building, on average 10% of productivity loss can be attributed to poor indoor air quality. 35% of absenteeism can be attributed to insufficient fresh air. There's an improvement of 29% with adequate ventilation. Again, these studies are from WELL and from other organizations. And then healthier buildings have a better ESG score, attracts better employees, customers, and probably more importantly for the building owners and investors. So while we were talking to our clients, they were asking us questions about, is there a return on investment in improving indoor air quality? So what we did for a couple of our clients, we did some very basic estimations and calculations. This one here is based on a 20,000 square foot interior workplace, about 100 employees, one person per 200 square feet, served by a single AC unit. So this is a simple cost of poor indoor air quality. So on average, 4 sick days per year per person. 1.5 days of those can be attributed to poor indoor air quality, with average industrial wage of $75,000, equated to $36 per hour. The loss to this employer for 100 people is on average $43,000 per year, which is considerable for just for absenteeism. So what we did was we actually did these installations as well. We took an estimation of how much it would cost to do a major improvement on this 20,000 square foot space. So at $40 per employee per year, which is average, and it's going to change depending on the region for increased ventilation air. $1,000 per year for increased filtration in terms of going to MERV 13 and maybe additional filter changes during the year. $20,000 for UVGI, a soft cost of $15,000. That equated to a total initial cost of $40,000, which is, give or take, was plus or minus 15–20%. It's in and around a payback of 1 year, which is pretty good. And that's just based on absenteeism rates. When you increase, there's been a lot of studies being carried out over the past couple of years in terms of increased productivity with increased ventilation rates. And there is a metric out there, that the increase in productivity can be equated to $4,000 to $5,000 per person per year, which is considerable. So it's really worth discussing with our clients how we can do that. So just real in conclusion, again, building owners are concerned about the impact to carbon emissions and therefore to local law 97 fines from all these initiatives that were carried out during the year. We're seeing a lot of demand for verification of the improved indoor air quality with monitoring systems. There are financial benefits from improved indoor air quality. And again, when we talk to clients, that's been talked about before, cost is a major factor. It's a real, both for indoor air quality improvements and to lower carbon emissions. There was a major capital investment on behalf of the building owners. And again, some of this can be offset using local and state initiatives. There's also really generous federal tax incentives through the CARES Act and Section 179 and 179D that gives the buildings some very generous tax deductions when they file the buildings. And that's it. Thank you.
Fantastic. Thank you, Desmond. I am now going to turn it over to John Rice, who will be our last panelist presenter.
Okay, assume you can hear me and see my screen. Are we good? Everyone can hear me and see my screen?
I can hear you. I cannot see your screen yet.
Let me see. Did I have to something? Or were you gonna? No one can see your screen. How about?
You should. There you go. Very
Okay, good. Thank you, everyone. First, I want to thank my former colleague and partner, Jeff Rios. He did a really good, broad introduction of electrification, and we're going to build on that just a little bit with a couple of specialized emerging technologies that apply to electrification. I got a short bio here in me. I'm President and Principal of Legacy Engineers, past President of ASHRAE. I sit on the board of the Urban Green Council. Okay, so I want to start out just by discussing hybrid air source geothermal heat pump systems. And here's our value proposition. So as Jeff was giving you an overview, air source heat pump systems are highly efficient, but typically they're highly efficient in the normal weather bands, say from about 40 degrees to 80, 85 degrees. And when you get in the extreme cold weathers and when you get in the extreme hot weathers, they start dropping off somewhat in efficiencies. Geothermal heat pump systems are efficient. They rely on the ground temperature, which is stable, 55 degrees year round. However, wells are very expensive to drill. So these hybrid systems, they do exactly what they say. They're a combination air source heat pump system, and then they also have this auxiliary loop in here that could be attached to a geothermal well system. And so you could use them for air source for most of the year, and then you could size a smaller well field. The barrier to geothermal is the upfront cost for all the wells. So with this approach, you could use air source for most of the year and have a smaller well field size to give you premium efficiency throughout the year. So let's take a case study number one. This is for a university client. This is a 5-story classroom and office building, original 1964 building, about 92,000 square feet. It originally had a steam absorption chiller in it, but it was replaced some years ago. It has a 300-ton centrifugal chiller, and it uses campus high-pressure steam. It converts that high-pressure steam to hot water, and so it circulates chilled water, hot water to perimeter fan coil units on the 2nd and 4th floor classroom spaces, and they have air handling units for the office floors on the 1st floor and the 5th floor of the building. So the first thing that we want to do to evaluate converting this building to a hybrid air source geothermal system versus the well field size. How many wells can your site accommodate? Here's our building right here. It has this nice outdoor space beside it. And taking a look at this, depending on the spacing of your bores, between 18 and 20 feet, we feel that it could get a maximum of about 28 bores on this site here. Now, you could potentially get more if you drilled wells into the sidewalk surrounding the building, but then you'd have to get a DOT approval, more regulation. So this client had us focused just on a well field with the open space that they controlled. I like this chart here because we call this chart the diminishing return on the well field investment. And it goes like this. This is geothermal capacity in tons, and this is the percentage of the overall heating and cooling load that can be accommodated. So if you look at it, the first 20 tons accommodates about 40% of the overall load. It would take about 180 tons to do the entire building if it was all geothermal. And if you look at that last 20 tons, you're almost getting no benefit for it. Each well, closed loop wells, is about 2.5 tons per well. So for 20 tons, that's 8 wells. So what this also shows is if you look at the slope of this line, where the slope starts turning from positive to negative, that's going to be your sweet spot. So for this site here, we feel that our sweet spot would be right around here, which is 70 tons. And that's, I believe that's, if I'm getting this right, 28 wells would be the sweet spot for the investment of how many wells you would need. We did a thermal load profile of the building. This is the heating load, and here's your cooling load down here. This load in purple, it shows simultaneous heating and cooling load. This blows up what the simultaneous heating and cooling load is, and the number of hours where you have simultaneous heating and cooling. So what this, and this is in MBH, the vertical axis here. So what it shows for about 4 tons, for most of the year, you have simultaneous heating and cooling. And the sweet spot here would probably be around a 10-ton. If you had one of your heat pump modules that could produce both hot water and chilled water, and without rejecting any heat, waste heat, that would be your sweet spot. So our proposed solution for this site came out to this. So here's our unit. These are modular units. You could set them up in modules, and you could set up these valve assemblies in between the modules. So you could have hot water coming off one side, you could have chilled water coming off another side, and these valves would valve off which ones of the modules are producing hot water or chilled water. So the first thing that we had figured out before was that our sweet spot was about 70 tons of geothermal of heat pump capacity. It turns out that produced only about 30% of the annual heating, and it produced 70% of the annual cooling. We also analyzed that 10 tons would be optimum for the simultaneous module, and then that produced another 20% of the annual cooling and 12.5% of the annual heating. So that left about 500 MBH for our air source usage, and predominantly it has to pick up the rest of the heating load. So this just shows the distribution and what portion of the heating, air source, or geothermal for heating or cooling throughout the year. In the last slide, we show that there was a little bit of conventional capacity that was required. And I don't know if it shows up well on this, but at the very, oh yeah, this is it here. At the very peak, so a little bit of conventional capacity was required in this scenario here. And it could come from whatever you're using for heating up domestic hot water, or a little bit of electric if you didn't have anything else in the building. By the way, we had retained a geothermal consultant to work with us, and that was MEP Geothermal that worked with us and produced a lot of this analysis. So for case study number 1, in terms of energy reduction, this was the existing building consumption. It was about over 6,000 million BTUs a year. and we could reduce that to 1.5 million BTUs a year in energy reduction. As Jeff pointed out earlier, it's really carbon, it's not energy. And so we could get a 67% reduction in the carbon footprint going to the hybrid system from about 340 metric tons to around 110 metric tons of carbon. Now, in terms of energy cost, in this scenario, there was actually an increase in energy cost. And we have to do somewhat of a deeper dive into this. This university client, according to the data that we have so far, and we have to sit down and go through and make sure that it captures all of their costs. Their gas costs was 46 cents a therm, according to the data that we have so far. And I assume that they're purchasing in bulk. They have a high pressure campus a steam boiler system that produces for the entire campus. So with the high cost of electricity and the lower cost of gas in this scenario, as several of the panelists pointed out, that the switch to electrification could be more expensive. So just another quick study. This is a different local university client. This is a residential dormitory building. It was originally a 1930 building. It didn't have any air conditioning before. It's going to go over a gut renovation, has a gas-fired boiler, and it serves currently just hot water to perimeter radiators. The main concern that we had here and the university had here is how do they electrify their domestic hot water heating load? So we wanted to take a look at that. And obviously, residential dorm buildings use a lot of domestic hot water. So the first thing we wanted to do for them was just to analyze a solar thermal system. And this is a typical solar thermal system where you have solar panels up on the roof. It requires a large storage capacity because obviously it's most of the hot water is being used morning and evenings, and most of the hot water is being generated all during the daytime. So it requires that. And then in the wintertime, it has to be weatherized. So this scheme for weatherization, you could put a smaller drain down tank someplace local right below the roof level. So when it gets too cold outside, it could drain back down to the drain down tank. We worked with Atelier 10 on this project, and they did a solar study for us of the roof area. What this shows is that the peak solar incident on the roof is about 1,500 kilowatt hours per square meters. And then we were laying out possible locations for our solar collectors, and they were giving us what percentages of the peak based on the location on the roof. And it just showed the ones in the back. This one had another building over here that was a little taller. And you see the solar collectors are oriented due south. So south is this way here. And it just showed the optimum location for panels on the roof. And we figured that if we could get 32 panels on the roof, it would accommodate 50% of the building's domestic hot water load. The thing about solar thermal is that you still have to size your backup plant 100%, obviously for cloudy days. The other newer emerging technology that's out on the field that's good for solar, for domestic water heating, is CO2 heat pump units. So they work under a similar, vapor compression cycle. The refrigerant is carbon dioxide. Obviously, carbon dioxide has a global warming coefficient of 1, as where refrigerants could be in the thousands. So in this example here, with a 20 kW electric input, where you do simultaneous chilled water, producing chilled water and domestic hot water heating, you could get about 20 tons of chilled water producing 6 GPMs of domestic hot water heating. And so the chilled water is about 70 kW, domestic hot water 90 kW. For 20 kW input, this is a coefficient of performance of 8, the 160 versus the 20. And then for, you know, a New York climate where you're not using chilled water all year long, it would still be a coefficient of performance of 4.5, even if you had to use the air and just reject the waste heat. And, you know, ideally suited for, I was speaking with one of the developers who's doing projects in Atlanta and Birmingham, Alabama, and it's ideally suited for climates like that have hot weather for more of the year. And this is one of the manufacturers of these CO2 heat pumps, and just one of their diagrams, how they tie it into their building systems. You could tie into the same domestic water tank and tie into their chilled water loop. This one happened to be in Mexico, which is obviously a good climate for a technology like this. So that's my presentation slides. I'm going to turn this back over to Scott.
Thank you very much, John. Very much appreciate your time here, as well as everyone's time. We're going to open it up for questions as soon as I get this screen off. And in the meantime, we have Jeff Cullen's question from the last presentation. I would like all the panel members to answer this, especially you, Amy, from a resilience standpoint. So why don't you start off answering this question? Can you speak to the high global warming potential refrigerants typically used in these heat pumps and their impact on the environment? With these refrigerants being outlawed without drop-in replacements, what do owners do?
I'm going to pass the back on that one to Chris. I think
you can pass on to Chris if you would like. Chris?
Yeah, I think Chris is going to be more aligned with that one.
There's no, can you guys hear me?
Yes, we can.
Yeah. So it's continuously evolving, I guess, is the answer, right? So the refrigerants of yesterday, R22, are obviously still available, right? You can get R22 on the market. So if you have a piece of equipment that has R22, you can still get it. Even though it's not being manufactured through recovery of antiquated equipment, you can still continue to serve your piece of equipment. So as things migrate and become more efficient, the refrigerants are changing. The GWP is changing as time goes on and becoming better. So I don't think refrigerants are going to go away anytime soon. I think to John's point, though, we're going to be seeing other products like John. I'm curious to hear more about that the CO2 refrigerant product that you were talking about. So I think there's a continuous evolution of refrigerants. Hopefully, we'll get to a point where we don't have them and don't need them. But I think that's going to take a while, is my opinion.
Anybody else?
Yeah, Scott, I'll second that. I agree with Chris's take on that. I mean, it's not going to be anytime soon that refrigerants are going to go anywhere. Again, they're developing like they did from R22 and the other more harmful refrigerants, and I think eventually they will be eliminated. But it's not going to be next 5 or 10 years. It's going to be a progression.
So you see the clients sticking with their existing refrigerants as long as they're not R12 and R11.
Yeah, and again, it boils, unfortunately, a lot of this just boils down to cost. What is going to be the cost of your refrigeration machines are going to last 30, 40 years, maybe you squeeze 50 out of it. Are you going to expect clients to keep changing refrigerants, and they're going to be pushed back, and the cost is also that's their main concern, building owners.
Yeah, that's the only thing that I would add to that is that's where a lot of the technology and research is right now on refrigerants. At the same time, systems like VRF systems that use a lot of refrigerants around I had a client reach out to me recently that they heard that these refrigerants were going to change, and would that mean they'd have to change out their systems in the future? With some of the systems that they're putting in. So it is a concern, but it's at the front end of technology and research.
Very good. An interesting question that came up. your clients dictate where the building is or is going to be. And in some of those locations, natural events are going to occur. So how do you go through the process of evaluating that? Let's say if it's on the Jersey shoreline, or if it's in the California mountains, or if it's somewhere where experience tells us that there's a great concern. I mean, how does that process go? Amy, would you like to start?
Yeah, I can speak to that one. Thanks. So, I mean, first up is understanding what the site-specific risks are, right? So whether it's seismic if it's in California, or if it's on the coast on the New Jersey shore, you might be dealing more with storm surge. And then understanding also what the future risks will be. So how those flood elevations will change over time, considering the impacts of climate change and sea level rise projections. So then when it comes to your MEP equipment, or even the building structure, really we're wanting to make sure that we first are using the right criteria. So our building code right now doesn't require us to consider the impacts of climate change. The New York City Climate Resiliency Design Guidelines recommend that, but the New York City Building Code does not. So, I mean, we think it's our obligation to our client to at least let them know what and inform them of that risk and how it will change over time. And ideally, if they're on board, and often their investors and their banks are definitely on board, their insurance companies want to consider the future risks and not just today's when they're building or making upgrades to an existing building. Given that we already have the location of that building, we can design the equipment in a way that it will be able to withstand those loads and locate it within the building at elevations that will protect it. And so, I mean, we've been working with Molly and their team on some of the work in the past at NYU Langone. So let's say we've already got a building that we know is in the flood zone, and sometimes we're able to elevate that equipment up above the flood zone, both current and future, considering those climate change projections. But sometimes you're just not able to. So we've had to provide additional protection in place at those lower grades as well. So in that sort of case, we call it interior compartmentalization. So we basically design the structure around that mechanical electrical room so it would be both waterproof and able to take those higher flood loads in the future in case something happened that the building perimeter protection failed. So there are ways that we can build in that redundancy, particularly for the critical equipment, which I think is really relevant to this group.
Desmond, can you answer that, especially with that client you spoke about that has facilities all over the country? How does that discussion go from one facility to the next?
Yeah, I can. These are existing facilities, Scott, and in certain certain parts of the country, we've been involved in almost like environmental studies, or provided information so that environmental studies can take place. The nature of some of the, without disclosing who they are, the nature of some of their resiliency and redundancy does force us to think a little bit, not outside the box, but really force us to think about redundancy in services, and basically resilient design, especially of incoming services. So things like Amy have already mentioned, incoming electric service. Main switch gears are never on the ground floor or in the basements. They're always on a floor above in certain locations. Those things you just got to be very wary of. And then the other part of that is in terms of backup generation. If you're using fuel oil, back in Superstorm or Hurricane Sandy, where we found that there were unfortunately many fuel oil tanks were floating around in the basements of some buildings. That was something that we really had to include in our designs. In other parts of the country that do have more frequent storm surges and flooding.
John? John, can you hear us?
Oh, yeah, no, I could. I didn't know if it looks like you froze a little bit. No, on the resiliency topic, no, I think Amy and Desmond, they got that one. I'll pass on the resiliency topic.
Jeffrey?
Yeah, sure. I mean, I think a lot of what's been said makes sense. I think Amy referenced the New York City Design Guidance, Resilient Design Guide. That's something we've referenced recently. It's been a while where this has been a topic, but without having a good resource to kind of like think about future flood levels, future storm surge and rain events that we want to size, storm systems for, and temperatures that we want to design mechanical systems for. You're kind of flying blind a little bit, but that guidance from New York City does help sort of define some of those parameters. So that is something we've been using in discussions with our clients. I think that's from an MEP standpoint, that's a lot of what the focus has been. I mean, obviously locating equipment out of flood zones, that's been something that's been done for a long time. And making sure it's future flood zones and not current, I think is a key as well.
Thank you, Jeffrey. Chris, would you like to add?
Yeah, the only thing I want to say, just kind of adding on to what everyone else has said, is that, when we're talking about energy efficiency and today's topic, electrification, I think we're hearing a lot of people use resiliency as like an excuse not to electrify. Like I don't want to give up my gas service and my boiler. I'm afraid to put in air source heat pumps and geothermal. I'm afraid to not have two energy sources to heat and cool my building. And I guess I would just want, I kind of, I understand the concern, but I would like to push back on that. I think we're headed toward a pretty significant investment in our electrical infrastructure over the next 10 or 15 years, and it is the future, and it's a must-have. And so I guess our challenge is going to be how to design buildings in such a way where they get a single power connection and the building still has the same level of resiliency as it did before, whether it's energy storage or backup systems, or I'm not sure, but I think we need to be thinking about electrification and resiliency too.
Yes, Scott, if I could, Chris did raise a thought here. In the dormitory project that we were just looking at, we did have a resiliency strategy for the project that we used to use before the big focus on carbon, which was you have a dormitory building, and in case of a power outage, the emergency systems in the building typically run for a certain period of time, and the strategy was to evacuate the building. Resiliency, you want to be able to shelter in place. So our strategy was to be able to keep, all your emergency systems on and keep heat in the building and allow them to be able to shelter in place. And then to use something like a microturbine that could, run all the time and pay for itself with its use, but then back up those emergency power systems. But the university client obviously didn't want the burden of the fossil fuel use for the microturbine, but they did want us to start researching things like battery storage. And so we do need to start seeing how some of those technologies will apply to building level projects.
Yeah, I would assume that battery storage has a lot of issues with space, ventilation, maintenance, situations like that. I would assume solar panels have a problem in high wind areas or high dusting areas, perhaps in California, where you have these wildfires. Are there any don'ts that the five of you can recommend? Don't put solar panels on an ocean front property because of the corrosive effects of the salt water. Are there any real don'ts that we should be looking out for? Don't put new cooling towers in an area that has a lot of pigeons flying around. Don't put all of these rooftop air-cooled chiller units on roofs that are located in areas like Phoenix that get incredibly hot to the point where airports are grounded because of the heat inversion that occurs in some of these areas. Are there some rules of thumb here when we look at implementing resilience and keeping our eye on energy?
Scott, you just answered the question for us.
Oh, no, I have
just
no
gave them all.
answers. I only have questions. You guys are the experts and you are talking directly to your clients. So how do you talk to your clients about this stuff?
I mean, this isn't like a secret or a trick, but I think, you know, these solutions are all, you know, John, your solution's highly integrated in terms of the geothermal and the air source heat pumps, and they're complex and they're challenging. So I guess this isn't a secret or a trick, but you know, it's about taking your time and really sitting down with the client and making, you know, having everybody understand exactly what you're doing and how the system's going to interact, what the new maintenance strategies are going to be, where do the air source heat pumps go, what does that mean in terms of the roof, the geometry, the structure, the adjacent buildings for noise, the thing that you brought up, Scott. So, I mean, it's not a trick, but I think we do need to go a little bit slower, and we do need to, there's a little more purpose on the HVAC than there ever was before. It's not just a, you know, rule of thumb solution anymore, right? There's a real integrated, you know, strategy that has to be implemented for each project, and it's unique to the building and the client. So it's definitely, the ante is up significantly.
The ante is up. That is a nice term. And Amy showed a slide that really showed the great benefit of that early being brought in the early planning phase, not get to design. Are you seeing that? Is everyone seeing that you're being brought in earlier in the process? Amy?
I suppose I'm preaching that as something we would like to see more of. There are times we get brought in pretty late, and that's it makes it much more challenging both for us and for the client and the rest of the design team. But yeah, I mean, when we get involved, particularly in the master planning feasibility stages, I think that it's much more productive for everybody.
Yeah, I think everybody agrees on the call that, you know, the earlier that you're involved in the planning stage, the far better for the client and the far better for the success of the project.
Yeah, I think engineers' skills have, I think that we're asserting ourselves in a wider part of the project now. Maybe in the old days, conceptual design, we'd lay back a little bit and let the design settle out. But now I think we're starting to get more engaged. You know, to your earlier question about the don'ts, I think Chris answered that correctly, that it's not so much don'ts, but, you know, every situation has challenges, and it's just how do you mitigate those challenges? You know, you talked about, you know, being located close to the ocean with salt water, and then you use certain types of materials on outdoor equipment. We get that with geothermal heat pump systems sometimes. We would often do open loop geothermal heat pump systems, actually using the groundwater. And then what we found out that over time, especially if some of these high yield well systems where you're drawing water from some wells and dumping them back someplace else, over time, you're changing actual, you know, the water chemistry. So if you started doing, you know, water analysis at the beginning, 2 years after running that system, that water analysis could be considerably different. So, you know, there's always concerns that you have to take into account when for any design application you're doing.
Anybody else on that?
I'll just agree with what I think most of us have said, but yeah, as we look at more newer technologies and or different technologies, right, we have to be involved early. The concept of a building has to be laid out to incorporate technologies that need different things than, you know, a boiler. Right? Like they need more space. They need to have access to that outside. They need to be located out of a floodplain. There's things that are changing. I think earlier involvement is important for that perspective.
Nice, thank you. So one of the real issues going forward is going to be, you know, there's so many innovations, so many new technologies that are coming on board. I wasn't aware of the CO2 heat pump, and that seems like a real innovation. I can't imagine you do geothermal, or maybe you do on Long Island, which was drastically flooded during Superstorm Sandy. What are the new technologies that your firms are looking at today, whether it's resilience strategies or sustainable strategies, like the CO2 pump? What are the other strategies that have come about in the last year or two that your clients are interested in hearing about, and financially it seems reasonable to implement? Desmond?
Just in the last year, Scott, again, going back to COVID and healthy buildings, we've had many conversations with the clients, different conversations forced, because the last year has forced our hand and forced everybody's hand in terms of how do we make, in terms of resiliency and almost safety, how do we make the workplace and buildings safer and better for people to come back into and working, with their, with them feeling confident and good about it, and that, really start getting into the healthy building designs, and that's why I mentioned, all the IAQ monitoring, the real impact on the indoor environment to productivity, absenteeism rates. And when you have those conversations with the buildings, facility owners, facility managers, it's always a very positive conversation until you get to the ultimate, which is the cost of the cost of and impacting local law 97. We're seeing at the moment where we're doing studies for buildings. How do I improve my my Energy Star grade? How do I reduce my carbon emissions so that local law 97 isn't going to be such a burden on the building? And we're there's concerns with capital costs, and there are incentives. There's plenty of tax incentives out there. The federal tax laws have been pretty generous for taking 100% deductions in the first year, and the CARES Act and 179D. So there's a lot of conversations that we're having with buildings. When it gets around to cost, we have to be a little bit more imaginative and think a little bit outside the box. But it is a challenge.
Scott, I was thinking about your question there, and I think if I could kind of break it down in like two categories. One is like the things that we can do now that move the needle in terms of energy use, and there are a lot of there's so much innovation right now, like on energy efficiency equipment, with whether it's new types of heat wheels or heat recovery coil technologies we're seeing a lot of, and obviously there's tremendous innovation on the heat pump and the heat pump market for domestic water and for air source heat pumps for HVAC. I mean, there's so much happening there. And that can definitely reduce energy on an annual basis and reduce carbon then if you're electrified. But then there's like another sort of turning point I think that we need, and that could unlock a whole bunch of other stuff. So right now Local Law 97 is an annual compliance period. It looks at annual carbon emissions, and it does not incentivize anyone to do peak demand load reduction or load shifting or energy storage. And quite the contrary, any energy storage actually hurts you from a Local Law 97 penalty perspective, because it increases your annual utility consumption and then therefore carbon emissions. And so, there's a lot of talk about some modifications to the law and potential tweaks to sort of allow for time of use based calculations as opposed to annual calculations. And if that's the case, I think that could unlock a whole entire opportunity for many other technologies and products, like whether it's phase change materials in the space, right, in the ceiling tiles or in the furniture or in the interior construction, or ice storage or battery storage, or smart grid technology and integration of appliances and PCs and computers to help do load shifting and peak demand reduction. There's so much technology that's out there that we can't make a case for here in New York City, because it actually makes you worse off with regard to Local Law 97. So I don't know, I'm hopeful that things can get tweaked. I know there are a lot of people that are interested in that. And if that's the case, then there'll be a lot to talk about, because I think it'll open it up even to more things, and really, again, up the ante even more in terms of what we need to do to make these buildings high performing.
Yeah, I agree with Chris as well in terms of Local Law 97. I think it's if you incentivize, if you make some of these local laws more positive in terms of incentivizing new ideas, and instead of being somewhat punitive, I think the technology will pick up a lot more. You get further down the road quicker.
So you'd consider Local Law 97 currently more of do this or you will be penalized, instead of this is a code, and if you go above this, you can be incentivized, whether that's tax breaks or rebates. Is that what we're talking about?
So the law right now is set up to measure annual building emissions, right? And so, and the only reason why that's the case is because the only data that's available in Energy Star Portfolio Manager is annual emissions, annual utility consumption. There's no benchmarking standard right now to capture data from a building on an hour-by-hour basis. And so that data is not available. There's no method for people to report it. There's no way to regulate based on it right now. And so because the law is set up that way with an annual basis, it just disincentivizes people to do energy storage, period, which is actually what we really need, right? We know that if you consume electricity at 2 o'clock in the afternoon, that's the worst possible thing you can do, because in the summertime, it's likely that electricity is being generated with the worst possible, fossil fuel generated plants in the city, right? These terribly belching, emissions power plants are serving your electricity during those hours. But the law doesn't currently incentivize you to eliminate power, eliminate consumption in that time period. So some major things have to change to get there. But if they do, like I said, that's going to create a whole other, sort of like, I think, opportunity for these technologies, which exist, but we're not using right now here in the city. I think it'll create a whole new market.
Matthew and I were thinking of creating a follow-up seminar. Do you like the idea of kind of a new technology, emerging technologies for energy use seminar in 4 or 5 months, sometime in the fall? Hopefully we're kind of pushed through COVID. Most of us are vaccinated by then. And at least in the US, hopefully we might be able to get ahead of this. Does that make sense to everybody?
Yeah, I was going to close out this discussion on technologies that, technologies, we're a lot reliant on the emergent technologies that are being developed by manufacturers. But if you look at innovations, the one thing that we do have, innovation occurs at the intersection of different disciplines. And, Sustainability 101 was the integrated design process and just better communication. We put these great teams together across all the various disciplines that come together. Just speaking more about your challenges and issues across the entire design teams and, finding the best solutions to innovate. But I think it's a great topic on both emerging technologies and innovations would be a good topic for ASHRAE.
Well, that'd be great.
Scott, I wanted to comment quickly on your question about punitive Local 97. I think it currently is, but as sort of as Chris is alluding to with some of the future things written into the law, there's the demand chart or the demand price of carbon, which is a big one. And then the other piece of it that there's potential there is the carbon trading potential, which would allow for this to not only be punitive, but incentivize people to do more so they could sell their carbon savings, right? I think that's we'll see as the laws and rules get developed that both those things moving are what we need for the solution we need ultimately.
That's extremely interesting. So we've reached 2 o'clock. I want to thank each of our panelists for your time, for your preparation, your expertise, providing it to the audience here. So thank you very much, and thank you to the audience. If you have any questions, email us, and we will get you answers. If any more questions come in your mind in the next couple of days. But once again, I want to thank all of the panelists. I know we're all very busy, and your time is extremely valuable. So I wanted to thank you one last time, and we'll sign off here. So thank you, everyone.
Great.
Thank you, Scott.
Thank you.
Thanks for organizing, Scott.
Take care.
Take care.